Okay, and we are live. Hi, everyone. Welcome to Fiveable Crams. This is our third night, May 3rd. Who's excited? We're all going to ace this AP Chem exam, for sure, for sure. So I'm here today with my fellow lovely student hosts, and we're going to be reviewing units 6 to 7. Tomorrow will be units 8 and 9, and then May 5th, remember, is our finale, where we're going to be doing a few FRQs, which is going to be really helpful for the AP Chem exam. Okay? So, some tips again before we get started. Take notes. You want to make sure that you're active during the whole session. You won't be able to remember everything you hear, so take little notes on what's important. You don't have to write everything down because you will have access to the video afterwards and you will have access to the slides. Second thing, remember, in your stuff section of Fileable, you have all the slides and replays available for you from tonight, the previous nights, the previews, all of that good stuff. Then next, use the group chat. Use it for sharing tips and tricks and like when we're asking different questions to participate. And then take advantage of our Q&A tab. This is a tab for asking questions. If you put in a question in the Q&A tab, our fellow student hosts will respond to you, and that way you can clear up any misunderstandings or any questions or any confusion that you may have, okay? And yes, we will take breaks. Also follow at Think Fiveable. Show us some love on social media, whether it's LinkedIn, YouTube, TikTok, or Instagram. And then some community agreements. Let's be supportive. Let's lift each other up. We're all here working towards the same thing. We want to get those 5s on our AP Chem exam, right? So let's lift each other up. And secondly, be patient. We have 5 nights together, even though some of the material you may know, some of the material you may not. And we'll get through all of it. Don't worry. We'll get through all of the important things that you need to know for your exam. And be patient. We have 5 nights. So we will get through everything. And then lastly, be kind. We're all real people, whether it's to your fellow peers or to your student hosts. Please be respectful. And then a little agenda. We did our welcome. We're going to go through thermodynamics, equilibrium. We're going to have a practice of everything we learned, a little Q&A, and then our closing. And remember, please use that Q&A tab for any questions that you have for our hosts. We have other student hosts on the live who are here to answer your questions. So, first off, we're going to get right into thermodynamics. It's 7 to 9% of the exam. So just a quick overview of the Unit 6 topics. You have the endo and exothermic processes. You have the energy diagrams. You have heat transfer and thermal equilibrium, heat capacity and calorimetry, phase changes, enthalpy of reactions, bond enthalpies, enthalpy of formation, and Hess's law. We'll get more into the bullet points. Those are more so for you so that if you notice, this is something that, I want to go back and you want to use the Fiveable question bank to practice a little bit more, this will help you out later on with like the structure of what we're going to go through. So we're going to kick things off with endo and exothermic processes. So with endothermic, the heat flows into the system. So endo is within. So another way I like to think of it is endo, the en. Also kind of you could think of enter. It also starts with an en. So it goes into the system. And the heat in this scenario is on the reactant side of the equation. So here you have like a little diagram, which would help you visualize it a little bit more. You have heat flowing into the system from the surroundings, okay? And then our opposites are exothermic processes. And this is when heat flows out of the system, right? So exo means outside, or I like to think of EX for in exo as exiting. So EX, EX, you have that similarity. So if you ever struggle with differentiating the two, remember endo, EN, enter, exo, EX, exit. Okay, and this is when heat flows out of the system. And then we have also a diagram for the exothermic processes. And like since when we have an endothermic reaction on the reactant side, when we have an exothermic reaction, it's on the product side. So here you'll see that it's going from the systems to the surroundings, right? So the surroundings are getting warmer. So pretty much the system, right? Because those are kind of like broad terms. The system is the stuff you're focusing on. So this may be solutions, it may be precipitate, it can be anything like that. And the surroundings is pretty much everything else around it, right? So you may have a ice cube in a cup, and everything on the outside is like the surrounding. So in the sense of the question, you'll kind of get a feel of, okay, this is the system and this is the surroundings. But the system is the stuff you're focusing on. This is what you're categorizing as endothermic or exothermic, and the surroundings is pretty much just everything else around it. Okay, so now a little bit more about the endo and exothermic processes. So for endothermic processes, the phase changes and chemical reactions are melting, vaporization, and sublimation, right? And also, so all of these involve heat entering the system, right? So that phase change, like when you're have an ice cube to water, it's melting. So that's heat is entering it, right? So you need to add heat for that reaction to occur. And in this case, reaction it requires energy to break the intermolecular forces or bonds. So a lot of times they will tie in like intermolecular forces or bonding into endo and exothermic like processes. So it's important to know that in these kinds of reactions, energy is required to break the bonds or intermolecular forces. Next up, we have exothermic. So in terms of exothermic processes, the phase changes are freezing, condensation, and deposition. Okay. And in these cases, you have energy being released when forming intermolecular forces or bonds. So again, you have that opposite of endothermic. To break, you need energy to break it, and in exothermic, you release energy to form it. Okay. And then the next thing is temperature changes. When you have an endothermic process, the reaction feels cold. That's because even though you're thinking of heat entering, wait, isn't heat entering? It's endothermic. It is entering, but it is being taken from the surroundings into the system. So since you're moving the heat from the surroundings and it's going into the system, it would feel quote unquote cold, right? And the thermometer would show a decrease in temperature, again, because that heat is flowing into the system from the surroundings. On the other hand, with exothermic processes, the reaction feels hot because heat is exiting from the system, right? So it's kind of like standing next to a radiator, right? If it's on, it's kind of like exothermic, not really chemically, but it could be considered exothermic because heat is exiting, right? So it feels hot, and thermometers will show an increase in temperature. So in the surroundings will feel warm, even though the system itself is becoming cooler. The surroundings feel hotter because of that exiting of heat. Lastly, enthalpy change. With enthalpy change, the enthalpy change of products is greater than the enthalpy of reactants for an endothermic reaction, right? So that means that delta H will be greater than 0 or positive. And a lot of times they'll tell you with the practice problems, with the FRQs, that they'll give you delta H and they'll tell you it's positive or it's negative. And that'll be a big clue as whether it's endothermic or it's exothermic. So make sure you know what delta H, like what the sign of delta H correlates to, right? So delta H is positive, right? So that means you are gaining heat. It's endothermic, right? And then on the other side, for the enthalpy of reactants is greater than the enthalpy of products for an exothermic reaction. And in this case, delta H is less than 0 or negative. Okay? Next thing, energy diagrams. You will have to draw an energy diagram on the AP exam, but they may ask you to describe different parts of it and recognize what kind of reaction represents. So take a quick second, look at the different parts, A, B, C, D, E, and think about it. Okay, what is this? And then in a few seconds, we'll switch the slides and we'll show you and explain everything. Okay, so now we're going to break up the parts of this diagram bit by bit. So A represents the reactants, right? So all the way on the left, right? That's always going to be the reactant side. It's going to represent the reactant part of the equation, regardless of where it is placed on that graph, right? That is always, always, always your reactants. And then we have B, and this is the activated complex. It's also sometimes represented by E sub A. So that's something to know, but they usually will tell you that it is an activated complex, or if you check on your chemistry reference table, you will find that explanation as well. Next up, we have C, the products, and just like with the reactants, no matter whether it's up here or down here, products will always be on your rightmost side, while your reactants will always be on your leftmost side. Next up, we have D, which is the I'm sorry, I made a mistake. B is the activated complex, and then D is the activation energy. So the energy it takes to get over that certain point to have the reaction occur. My bad. So D is the activation energy, and E is the enthalpy change, right? So that's the change, that's delta H, like we spoke about earlier. So now, is this in the chat? Is this reaction endothermic or exothermic? What do you guys think? Exothermic? Okay, yes, yes. So, um, whoever asked what was B, B is the activated complex, okay? It's on the screen, so everything's up there. So this reaction, like everyone says, is exothermic, right? So it's starting from a higher point and it's going down to a lower point, right? So the A and the C, so the C is lower, so it's exothermic. What I kind of like to think about when I see these different graphs is like a slide, right? So you're kind of like sliding out, right? You're not trying to go up higher, you're trying to like slide out. So you're exiting, it's exothermic. So in this case, when you have delta H and you have the delta H final minus the initial, which is the delta H of the H of the product minus the H of the reactants, delta H is less than 0. And what would an endothermic graph look like? What do you guys think? So an endothermic reaction pretty much is just the opposite, right? So instead of heat exiting the system, you have now products are higher than the reactants. So you have heat entering the system. Everything else is pretty much the same. The A, B, C, D, E are still defined by the same thing. But just notice that the exothermic reaction and the endothermic reactions are reverses of each other. Next thing you have to know is heat transfer or in thermal equilibrium, right? So if you have an isolated system, like shown in the boxed purple, that means that there's no heat transferred, right? If you have something in the freezer and then something outside of the freezer, they're isolated systems, right? There's no heat transfer between these two objects, like shown between A and B. There's no interaction, there is no direct contact, therefore, there is no heat transfer. Next, if you have systems in contact, a heat transfer can occur. And what's important to note is the way that heat flows, right? So you see box A, the red one, in the center, you have it flowing from a warmer object to a cooler object. So this is your higher kinetic energy to lower kinetic energy, also known as your higher temperature to lower temperature. And remember, on the AP chemistry exam, if they say the average kinetic energy, that just means temperature. Don't let them be like, wait. Kinetic energy, okay, Ke equals half mb squared. Average kinetic energy, if they ever say average kinetic energy, it refers to temperature, okay? So keep that in mind. So in this case, you have the transfer of Ke through collisions. And then the heat will continue to transfer until a thermal equilibrium is reached, right? So heat will keep flowing from the warmer object to the cooler object until they're both around the same temperature and they're at equilibrium. And that's pretty much when they're the same average kinetic energy or same temp, like I said, and there's no net change in kinetic energy, so that there's no more changes in temperature anymore. Next thing, heat capacity and calorimetry. This is a lot on the AP exam. Q equals MC delta T. And you don't need to memorize this formula. It is on your reference table, but you do need to know how to use it. So just to go over what the different variables represent, Q stands for the heat lost or gain, and this is in joules unless they specify otherwise. M is the mass, and this could be given to you in grams or kilograms. Then we have C, or delta T, I guess we're doing that first. Delta T is change in temperature, and this could be either in Kelvin or Celsius. And then C is your specific heat capacity. So joule, and that could be in joules per grams Kelvin or joules per kilograms Kelvin. And specific heat capacity, just to give a quick reminder, because they do like to use this in a few different ways, not just with this formula, but they may ask you, okay, this has a specific heat capacity of this, and that has a specific heat capacity of that, and like, why does this happen? So specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a sample by 1 degree Celsius or 1 kilogram sample by 1 Kelvin. So that's important to note. And then lastly, the higher the specific heat, the more energy it takes for the object to heat up and cool down. And then for example, water has a specific heat capacity of 4.84 joules per gram Kelvin, per gram Celsius, sorry. And metals have a generally low specific heat capacity and therefore are poor insulators. So that's important to know, and that may come up in different ways on your exam. So here we have calorimetry. You won't have to actually do this on your AP exam. They're not going to give you a cup and metal and say, go do this. Maybe you do that in lab, but you're not going to need to do it on the exam. But you do need to have an idea of what calorimetry is, right? So in this diagram on the right, you have a metal at 100 degrees Celsius, which is the system, right? And you're placing it in water at 25 degrees Celsius. And that is the surrounding. So metal obviously is at a much, much higher temperature, 100 degrees Celsius versus the 25 degrees Celsius. So when you place that 100 degrees Celsius metal in that 25 degrees Celsius water, what's going to happen is the heat will transfer from the metal to the water. So again, we see that from high temperatures to low temperatures, there's that heat transfer. So the metal will lose heat while the water will gain heat, right? So this is the first law of thermodynamics pretty much demonstrated. Energy cannot be created nor destroyed. It can only be converted from one form to another. So in this case, we have the heat from the metal being converted to the heat in the water, right? So we cannot just have like the heat suddenly disappear. We can't have that, 100 degrees Celsius to 25 degrees Celsius. Like we can't have just like a sudden change with no indication of where this heat went, right? And this is also known as the law of conservation of energy. So kind of like to put it in simpler terms of this diagram, any heat lost by one system is gained by the surrounding. So it has to flow in between each other. They cannot just like disappear. One thing that's very common you'll see is coffee cup calorimetry. You guys may have done this in your labs for AP Chem. And it's pretty much, as seen on the right, you have a thermometer, a styrofoam cover, like styrofoam cups, and you have the stir, and you're pretty much you're using this device to measure the enthalpy or heat changes. And the use of styrofoam helps prevent the heat transfer between the reaction and the surroundings. And any temp change is a direct consequence of the reaction, right? So you're pretty much isolating the system to make sure like no outside influences kind of affect it. And what would happen if the insulation were not perfect, right? So if the insulation were not perfect, then you would be risking a significant amount of heat being lost to the surroundings, and then you don't have an accurate representation of the heat change or the enthalpy change with that reaction itself, right? Because if you have heat seeping onto the surroundings and you're trying to gauge, okay, what is the heat absorbed or released in this reaction, you won't be able to get an accurate gauge of that since it's seeping out into your surroundings. Sometimes they may ask you, like with the lab related questions, what is an issue if the cup was unsecured? What will happen to the temperature, right? So this is like something to remember. If the system is not perfectly closed, not perfectly insulated, it allows maybe for heat to escape, for heat to enter, things like that, depending on the circumstances. Next up is phase changes. So phase changes require or release energy, okay? For example, like a heating or cooling sample, breaking and forming intermolecular forces. And here you'll kind of see that below. So you'll have, when you go from a gas to a solid, that is forming intermolecular forces, but in vice versa, if you go from a solid to a gas, is breaking intermolecular forces. And that's same thing with heating and cooling a sample. And for heating, use Q equals MC delta T. And make sure you use the right C value, right, for the specific heat. And then for phase changes, use delta T equal to 0. So Q equals N times delta H. And then for reverse phase changes, for example, melting and freezing, reverse equals negative delta H. Okay. And remember, phase changes, the reason why delta T is 0 is because the temperature doesn't change when the phase changes. Okay, so when you have that, like with your heating and cooling graphs, when you have that like plateau, that straight line, those are your phase changes, and temperature remains constant. Okay, you only have those temperature changes with the same phase. Okay, don't confuse those, because that may be something that trips you up, because you may think, wait, but you have that heat to have that phase change. In this case, no, when you have those phase changes, the temperature remains constant. So next up, with phase changes, here is a little the curves I was talking about, right? So we have the heating curve for H2O. So as you see for the part A, that whole time the temperature is increasing, it remains a solid. Only in part B does it go from a solid to a liquid, to allow it in part C to remain a liquid the whole time, right? So the areas which we would use Q equals MC delta T, right, where we have the value of the temperature, is parts A, parts C, and parts E, where there is a temperature change, where there is no phase change. Okay, that's where we use Q equals MC delta T. However, in parts B and D, that's where we do not, there is no temperature change. That's where the phase change occurs, right? And that's where we don't have that temperature. We have temperatures equal to 0, because there's, well, delta T is equal to 0 because temperature doesn't change. And which enthalpies of reaction, of transition, would occur at B and D? So at point B, you're going from a solid to a liquid. So this is the delta H here is the delta H of fusion. So it's from a solid to a liquid. Or if you're going the reverse way, right? So if this cooling curve was, if this heating curve was flipped to a cooling curve, then we would go from liquid to the solid, which would be the negative delta H of fusion. And at point D, we have heat of vaporization, because we're going from a liquid to a gas. And the same thing, if we were to take this heating curve and flip it into a cooling curve, then this would change it to a negative delta H of vaporization, from a gas to a liquid. Okay, and here's a different type of like graph to kind of visualize this. And here you see, it's kind of structured so that you can imagine the graph in both ways, right? So as you go from bottom to top, you have the melting, you have the vaporization, and as you go in the reverse direction, you'll see the condensation and the freezing, right? So how would you calculate the total heat gained by the sample from point A to point B? I'll give you guys a second. The first thing you're gonna do is add up all the Q's from A to B, right? So you guys may not, it may be difficult to see because the slides are a little bit small, but for each of the like the increases in temperature, right? You could see a Q value for all of the different lines. You'll see a Q value. And what you're gonna want to do is add up all the Q values in between those 2 points where you want to calculate the total heat gained. So now after you add up all the Q's values, what you'll do, in here we have it demonstrated, Q1 plus Q2 plus Q3, you're going to ask yourself, what state of matter is the sample in now? You're going to have a liquid, right? Because we see this is a heating curve. So we're going from the solid to a liquid. And now we're going to do a little FRQ practice, from the official College Board. So I'm going to read it, and then we're going to set a timer, and you guys are going to go off and try it. Okay? So, as part of the experimental procedure to purify the HC2, HC7, H5O3 crystals, after the reaction is complete, the crystals are filtered from the reaction mixture, rinsed with distilled water, and dried. Some physical properties of HC7, H5O3 are given in the following table. So, some properties of salicylic acid. The melting point is 159 Celsius. Solubility in H2O at 25 degrees Celsius is 2.2 grams per liters. The specific heat capacity is 1.17 joules per grams Celsius. And the heat of fusion is 27.1 kilojoules per mole. So now, with all that information, what they want you to find is, given the physical properties in the table, calculate the quantity of heat that must be absorbed to increase the temperature of a 0.105 gram sample of dry HC7 H5O3 with a molar mass of 138.12 grams per mole crystals from 25 degrees Celsius to the melting point of 159 degrees Celsius and melt the crystals completely. Okay, we're going to set a timer. We're going to give you guys some time to figure out this question. Try it through. We're going to go through it bit by bit, but see if you were able to retain what we went through. Okay, your time starts now.
All right, and while you guys are doing the FRQ, if you do have any little small questions, I can take this time to answer a couple. So if you do, hit me. If you don't, I don't know, I'll just stay here, I guess. It's cool. Hello. Hello, it's me. You miss me?
Oh my god.
Okay. Did I get... no, I didn't. I didn't. I didn't. I didn't have an exciting day today. I didn't do a whole lot. You missed my street sign? Listen, I was going to take it down because I was like, people are talking about it too much, but then I decided not to. So, I did not steal it. I did not. Okay, okay, okay. I would like one of those Bobo plushies. I have a little... It's not out right now. It's shoved in a suitcase and kind of depressed, but I have a small stuffed panda. I went to Nova Southeastern. When you use heat of fusion versus specific heat capacity. So the specific heat capacity is a constant C, and that is when you are within a certain change. So when you're within a solid and when you're going up that kind of solid curve and when something's absorbing versus absorbing or releasing heat, then you use specific heat capacity. Heat of fusion is specifically referring to across a particular phase change, and that phase change would be fusion, right? Yeah. Wait, Yasha's right. Yasha's right. I support. I am here to answer questions for all of 1 minute and 56 seconds, but then I'll answer more questions later. I'll yap some more. So. Periodic table song. I've not heard a periodic table song. I have heard some interesting AP Chem acronyms, though. I'm not allowed to say them, unfortunately. You can blame Anova for that one, though. Can you start a GoFundMe? I mean, I could use a GoFundMe for some couple other things, namely my medical school. But like, if you guys can only raise like $10, like the Boba plushie would do for now, that's cool. That is cool. All right. Neon to light up the sides. Are we getting... Please don't get through the whole song. I'm not going to lie. This is going to take the rest of this session. And this is all the chat's going to be. Is going to be like phosphorus, sulfur. I don't even know how the song goes. I don't even know. Anyway, guess what? Timer's up. So I'm going to stop talking. But we are going to go through the FRQ, okay? So if I can go through the FRQ. Okay, let's break this down. Let's hit the first question, okay? So given the physical properties in the table, we're going to calculate the quantity of heat that must be absorbed to increase the temperature of a 0.105 gram sample of dry HC7H5O3, which has a molar mass of 138.12 grams per mole, crystals from 25 Celsius to the melting point of 159 Celsius, and melt the crystals completely. So we're going to break this down, right? In general, when you see this question, you're going to see the things of, you're going to see heating, right? You're going to see a thermodynamic change in heating. You're also going to see a state change, right? Which means two things. A, it means we're going to use both the questions. And B, it means we're going to use the thermodynamic questions in the first place. We're going to use Q equals MCAT and the other one. That doesn't have a nice little ring to it, but bear with me. But yeah, so that means we're going to use those. And we know that we're focusing on thermodynamics. So we know that we're going to look at that part of the equation sheet. We know that that's going to happen. Like that's the thing that we're going to be focusing on, right? So what are our givens here? Okay, right? We're given obviously the molar mass, and we're also given the sample in grams, which means also you should know right off the bat that you can calculate the amount of moles of things that you have if need be. I don't know if need be, but if need be, right? And we also know a beginning heat. We know an initial heat of 25 degrees Celsius, and we know the ending heat of 159 Celsius. We also know that a phase change has occurred because we are trying to melt the crystals completely, right? And then we also have like a little like properties list over here, but that also gives us a lot of constants. It gives us the specific heat capacity. It gives us 1.17 grams per joules per gram Celsius, and the heat of fusion, which is 27.1 kilojoules per mole. And I would encourage you to look at the units and pay attention to the units and notice that the specific heat capacity is given in joules as part of the units, and a heat of fusion is kilojoules. So those are different. Okay. You're also given some other things. You're given things like solubility. You're given things like melting point, which it also says in the question. But remember that they do oftentimes give constants, things like that, like givens that are not used in the question. And that is okay. So don't freak out. Be like, oh my God, I'm not using one of these, but I have an answer. So I don't think the answer is right. That might not necessarily be true. Okay. So we're going to calculate. Okay. We have two things here. We have a heating and a melting occurring, right? So that means we're going to use both our equations. So our total is going to be the addition, the amount of joules of energy from both the equations, right? So in the end, we know that we're going to add these two things together. So let's look at the first one, right? We're going to use our MCAT equation. Our M is mass in grams. Our C is the specific heat capacity, and our delta T is our change in temperature. So we're going to just plug and chug, right? We're going to have our mass is 0.105 grams. Our C is 1.17 joules per gram Celsius. And our change in temperature is final minus initial. Remember that, not the other way around. Our final is 159 degrees Celsius, and our initial is negative 25 degrees Celsius. Do our calculations, we get 16.5 joules. And then, remember, we're not done, right? Because this question said that we're going to melt the crystals completely. So we need to look at the heat of fusion, which is, like Yash just said, is a fancy way of just saying melting. So in that case, we need the amount of moles times the heat of fusion, right? And we know this. And if you're like, oh, like, do I need the grams or do I need the moles? We're going to look at the units of our heat of fusion. Our heat of fusion is kilojoules over moles, right? So you need moles. So that means Q is 0.105 grams. And then we're going to convert that from grams to moles of what we're talking about. So we're going to use the molar mass and then multiply it by 1 mole over 138.12 grams. That's stoichiometrically. And then after that, we're going to multiply that by the heat of fusion. Remember, if I was to multiply it by the heat of fusion that was given to me, that is 27.1 kilojoules per mole, I will get an answer. It will not be wrong. It also will be in kilojoules. And if I add kilojoules and joules together, that's when it'll be wrong, right? Heat of fusion is given to you. Yeah, it's in that table. So we're going to convert it to heat of fusions. We're going to convert it to joules over mole first, which literally just means take the 27.1 and multiply it by 1,000. So it's 27,100 joules per mole, right? So once we do all our math over there, we end up with 20.6 joules that is how much energetically it took to melt the crystals. So what's our total energy? It's pretty easy now that we have both the heat and we have the melting. We're just going to add them together, and we're going to get 37.1 joules. Get it? Got it good? So isn't it negative? So it's actually, so look at the question, right? So the question says that you need the heat, the quantity of heat that needs to be absorbed. And so if you're absorbing, you are injecting heat into the system, which means there will be a positive heat. So once you're injecting energy into the system, it will be positive. Right? It does not matter whether your answer is in joules or kilojoules, but you must be consistent. You can't calculate the heat in joules, and you cannot calculate the melting heat or the melting energy in kilojoules and then add them together. That will be wrong. Okay? So just remember, the units are fine as long if it's kilojoules, joules. I don't know if you want like another one. If you like megajoules, like I'm gonna send you to a psych ward, but like that's fine. So whatever it is, just be consistent. Okay? That is the end result. We're good? Yeah, QMEL is not, so the heat of fusion specifically is the unit of 27.1. That is molar. QMEL is the energy. We're calculating how much energy it requires to melt it. We use the heat of fusion to calculate that. They're not the same thing, but we are using the heat of fusion to calculate QMEL, which is how much energy is required to melt it. Exactly. Right? We're good? Heat of fusion is both, actually, technically. It just depends on which way you're going. Okay, heat of fusion can be used to melt or solidify the substance. It is dependent on which way you're going, and that will depend on either how much heat is released or how much heat is injected, or how much energy is released or how much energy is injected into the system, depending on what state its surroundings are at. So heat of fusion is both. Okay? All right. Okay, let's move on. Hope that FRQ went well. Manifesting that it went well, because I don't actually know if it went well, but I hope so. All right, let's talk about enthalpy. What is enthalpy? Enthalpy is heat energy. We represent it by H. However, do we really care how much what enthalpy really is? No, not really. What we do care about is the change in enthalpy, our delta H. That tells us whether heat is released or absorbed by a chemical reaction, and it has to be given at a constant pressure. On AP Chem, when you're doing it, just because they don't typically like mix like thermo with other things, you can assume that if you're dealing with a delta H, it is at a constant temperature. Like that's generally a completely fair assumption to make on the AP Chem exam. So don't worry about that too much. And yeah, and remember, it is an extensive property, which means it is affected by how much of the reaction you're doing, like what's going on particularly. And yeah, so the overall enthalpy of a reaction, or delta H sub reaction, is the sum of the amount of moles times the delta H of the products minus the amount of moles times the delta H of the reactants, right? So everything has a particular enthalpy. Every substance has a particular enthalpy. And our overall enthalpy of the reactions will be the enthalpy of the products minus the enthalpy of the reactants. And if that ends up positive versus negative, it tells us something, right? If it ends up negative, it's exothermic. We'll get into that. And if it's positive, it's endothermic. But that tells us something about the reaction. Yeah, and N and M are just stoichiometric coefficients. It depends on like how much of each, like how many moles of each particular thing you're using in one instance of the reaction, right? And like I just said, if delta H of the reaction is greater than 0, you have an endothermic reaction. And if delta H of the reaction is less than 0, you have an exothermic reaction. Okay, let's look at a quick little example. So in this example, 1 mole of CH4 or methane gas is reacted with 2 moles of oxygen. This is a combustion reaction, by the way. If you were here yesterday, I hope you can see that as well. Just to draw a little conclusion. Anyway, so you have 1 mole of methane and 2 moles of oxygen that are reacted to make 1 mole of carbon dioxide gas and 2 moles of liquid water, or H2O. Right? Our delta H of the reaction in this case is negative 840.4 kilojoules. Let me know. I'm looking at the chat. Is this an exothermic or endothermic reaction? Talk to me. Yes, exothermic, exothermic, exothermic. Exactly, 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 exactly. Perfect. So practically, this is a very commonly asked question. How much heat would be created if we were to react 79.2 grams of oxygen? So in order to do this, we need to convert grams of oxygen into moles of oxygen, right? Because we need to know how many times this particular instance of the reaction is running. And when I say instance, I know that might sound confusing, but an instance just means like in this case, it requires your reaction requires 1 mole of methane gas, like CH4 gas, for every 2 moles of oxygen used, right? So we're not talking about how much we need in grams, we're talking about it in moles because that's what like is interacting to cause the reaction. So that's why we need to convert it from grams to moles. That's why you just can't use grams, just for like a quick little explanation. So we can convert it. And then what we can use is we can, excuse me, almost choked. So then what we can do is we can use the kilojoules of heat of the reaction, and then we can divide it by the amount of moles of O2 that we're using, and we can stoichiometrically figure out how much heat is created by reacting 79.2 grams of oxygen. So the grams of oxygen are first converted into moles of oxygen, right? And then they're multiplied by our enthalpy of the reaction. Now, you might ask, like, oh, like, why is it negative 840.4 divided by 2 moles of 2 moles of oxygen? And that's because the enthalpy is per rate of reaction, right? So this negative 840.4 kilojoules, that's how much energy is released every time one instance, like I just said before what an instance was, of this reaction like runs essentially, or like happens, which means for every 1 mole of methane, for every 2 moles of hydrogen, for every 1 mole of carbon dioxide that's produced, and for every 2 moles of water that is produced. That's how much that's what this negative 840.4 kilojoules is. So it's negative 840 kilojoules per 2 moles of oxygen used. So that's why we can use that and multiply it by the amount of moles of oxygen, that is 79.2 grams, and we can figure out how much heat is created by specifically reacting only 79.2 grams of oxygen. Does that make sense? I understand it's like a little bit convoluted to understand, but it's really important to get this. This is something that I've seen a whole lot, and I'm pretty sure that you guys will see. Okay. And yeah, okay, yeah. So just to like round for sig figs, this isn't rounding for sig figs. I lied, but I guess it's rounding off. But for that, it's about 100 or about 1,100 kilojoules of heat released. Okay, so let's talk about bond enthalpies. Okay, so breaking bonds requires energy, and forming bonds releases energy. Why? Because forming bonds is typically more energetically favored than breaking bonds. Breaking bonds requires work. Bonds form when they're in, correct, when they're in correct orientation, which is spontaneous and therefore releases energy. Okay? Yeah, like the hit TV show Breaking Bond. Oh, that's why they had the emoji. See? That's kind of funny. Anyway, apparently that's an acronym. BARF. I've never used that, but if it helps you, that's cool. Breaking is absorbing and releasing is forming. Okay? I also just I would encourage you to think about like why it makes sense and just logically think about it. And breaking requires like work, right? Because you're like taking something that's already present and breaking it apart, and then forming is almost spontaneous. So it typically releases energy because it is energetically favored for it to occur. And it's more stable to bond. Okay. Bond dissociation energy is the amount of energy a system requires to break any given specific bond. If a certain molecule has more bonds, it will have a greater bond dissociation energy, right? Like if you have a really large molecule with a whole lot of connections, a whole lot of bonds, it will have a higher bond dissociation energy than a substance that is only like say single bonded. A carbon monoxide versus carbon trioxide or something like that. And then shorter bonds are also stronger bonds. We know this based on periodic table trends, right? So shorter bonds are typically stronger, and that also means the bond dissociation energy is increased. And then enthalpy. What that means is the enthalpy of a reaction is the sum of the energy of the bonds that you had to break minus the sum of the energy of the bonds that you had to form. This is just another way to calculate delta H of the reaction. There's a lot of there's a couple ways. This is one of them. Another one was like the one that I literally just went over like the last slide, of like the specific heat, like the enthalpy of any given substance in a particular reaction. Okay, so you want to do some math? Find the delta H of the reaction this is the same reaction that we just talked about. So find delta H given some substances in the table. You have the bond energies, the bond dissociation energies in the table. You also have the bonds drawn out for you, but generally you should be able to draw them yourself, just as like a little FYI. Because these are relatively simple ones. They're not like too detailed on like how you have to draw, especially organic molecules like on the AP exam, but generally the simpler ones you should definitely know like what's going on. Okay. So I hope you started it. I can't give you a whole lot of time because we do have to keep moving, but I hope you started it, or at least have a good idea where we're about to go, because then we will talk about them together. Okay. Yeah, and like I said, just draw out the Lewis structures quickly first. It helps to like really organize like what like bonds are breaking, what bonds are forming, like what is specifically going on in this particular reaction. Don't try to do things like this in your head. It's just not a good idea. Okay? You're not cool. Just don't. Maybe you're cool. I don't know. But yeah. So what is delta H? Delta H is the sum of the broken bonds minus the sum of the formed bonds. Right? So we're going to break these down. What bonds broke and what bonds formed? The bonds that broke are the bonds between C and H, and also the bonds between the oxygens, right? So they broke. But how many of them broke? That really matters as well. Don't forget about that. It's a really common mistake how many bonds broke. You have 4 CH bonds that all broke, and you have 2 of the double bonds between the 2 oxygens that broke, right? And then what bonds formed? Well, you have a double bond between carbon and oxygen, but how many times did it form? Not just once, but twice, right? Because it's carbon dioxide, not carbon monoxide. Yeah. And then also, you have the bonds between oxygen and hydrogen in water, right? You might be given a bigger table. You might be given things that are unnecessary. For example, this one, like 3 down, like the bond between carbon, like a single bond between carbon and oxygen, that has a dissociation energy of 358 kilojoules per mole. We don't use that. Don't try to use everything. That's why drawing out the Lewis structures is important, because if you didn't, you might be like, oh yeah, carbon and oxygen are bonded. And then you might just look at the first one that you see, which is that one, and then use that. That's wrong, right? So draw out the Lewis structures. Notice how many bonds. Is it a single? Is it a double? Is it a triple? Probably not, but it might be. Like an HCN. Stuff like that, right? And then we're going to do our math. So we plug and chug, right? CH 413, oxygen 498, the CO double bond 799, and the oxygen hydrogen single bond 463, right? And then we do our math. Boom, 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 boom. Negative 802. Someone said it. You're cool. You get me? You're cool. But units exist, right? Remember, broken minus formed, not the other way around. If you get the other way around, you get the same number. You won't get the same symbol, right? You won't get this, or symbol, sign, I'm sorry. You won't get the same positive or negative, right? So remember that the bonds broken in this reaction, the bonds broken were less energy than the bonds formed. That's why our delta H was negative 802. The coefficients, right? That's why we said like 4 CH and 2 OO, right? The coefficients are just how many times this occurred, right? You have 4 CH single bonds, but you only have 1 CH4 total in this particular reaction. However, the oxygen is just one, like each oxygen, O2, is just one double bond between the 2 oxygens, but you have 2 of them because we have 2 O2s. That's why we accounted for 2 O2s, and that's why we did 2 times the 498 that is in the oxygen. That's where the coefficients are applied. Same thing with water, right? Why did we do 4 OH bonds? Because each water is 2 OH bonds, and we needed 2 of them. That's where the coefficients are. Kilojoules over mole is required. That's the heat of the reaction is negative 802 kilojoules for every mole of the reaction that's occurring. It is the correct form. Yes, yes, yes. All right. Enthalpy of formation. So the standard enthalpies of formation is the amount of heat needed to form 1 mole of compounds for the elements in their standard state, right? For given elements, the enthalpy of formation is 0. Like you'll see on that table, the second one down, O2 gas. The heat of formation is 0. Okay? This is just a definition. I would encourage you to know it. And yeah. So the heat of the reaction, this is an equation that I gave to you not like, a handful of slides ago. The heat of the reaction is the sum of the heat of formations of the products minus the heat of formations of the reactants, N and M being the coefficients of any particular substance in that reaction. Okay? It's just another way to calculate delta H of the reaction. Bond dissociation is just as correct. It's not different. It is correct. It's just a different way of going about calculating the same enthalpy. Same change in enthalpy for the reaction. Okay? You would just calculate, like, before someone inevitably asks, which one do you use? You use the one based on what things you are given. If you're given enthalpies of formation, this is the one that you use. If you're given bond dissociation energies, you use the bond dissociation ones, right? Unit broken minus formed. Okay? All right. Example time. N and M are the coefficients. N and M are the coefficients in the reaction. How many moles of each thing you require? Example time. Same reaction that we just did, but this time we have some different information, right? This time we have the enthalpy of formations of each substance. So, yeah. So we write out our equation, like I just said, it was delta H of the reaction is the sum of the enthalpies of formation minus the enthalpies of formation of the reactants, N and M being the coefficients and how many moles of things that you're dealing with. Right. So in this case, what substances do you have? What substances on the product side do you have? You have H2O, and what else? You have CO2, right? So how many H2Os do we have for every one instance of the reaction occurring? We have 2 moles. 2 moles of H2O in this particular reaction. So we look at our enthalpy of formation table that they would give us. You're not expected to know any of those like off the top of your head or anything. Don't worry about that. So you would use that, and you'd use negative 285.8. And the N, Anya, here's your question. The N and the M, the N in this case is the coefficient of the reaction. The coefficient. So how many waters do you have? How many H2Os? 2. How many CO2s? 1. And then you do the reactants, same deal. Your reactants are CH4 and oxygen. Remember, O2 will be 0. If you have another substance like that, if you have H2, same thing, 0. Okay? Just make it a little easier for you. And then you do the math, and yep, there you go. Negative 890.3. Listen, okay, if I go back to this chart, I'm sorry, if I don't go back to that chart, that was an accident. I thought there was something else back there, but that's fine. Okay, but yeah, so negative 890.3, there you go, there you go, there you go. Exactly. So the enthalpy of formation based on the formation delta H's of the reactants would be negative 890.3. Negative meaning it's what? Exothermic or endothermic? Exothermic, right? The units are kilojoules per mole. Yeah, joules per mole. It's generally joules per mole. This is a kilojoules just because we're talking about that, but like, yeah, joules or kilojoules or some other form of joules over mole. Yes, exactly. It's exothermic. Yes, 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 yes. Yes, bonds when formed to release energy to the environment, to the system. Okay. All right. All right. Let's talk about Hess's law. So Hess's law uses enthalpy, and it's reliant on the fact that enthalpy is something called that we call a state function, right? What does that mean? Well, state function basically means that you're only looking at the beginning and the ending result. It's a change. Delta H is a change. It does not depend. We don't care about the path taken to get from the initial to the final state. We don't care about the path that any given enthalpy, that the enthalpy of the reaction took to get from the beginning to the end. We just care about the fact that there is a beginning and their end, and that's what we subtract. We subtract the end from the beginning in order to find the overall delta H. You guys like Hess's law? Okay. I don't know, it has a lot of clout. It is satisfying, I guess you're right. But yeah, so you can use multiple subreactions to find the delta H for a composite reaction. And that's kind of where we derive Hess's law from, and that's why we use Hess's law. Hello? Oh yeah. So when you reverse a reaction, do remember that you flip the sign of delta H. Okay? And when you multiply a reaction by a given number of moles, that means you also have to multiply the delta H by the number of moles, right? We said that enthalpy, we said a little bit earlier that it is dependent on the amount, and this is why. It is dependent on the amount of moles. you do multiply it. If I need like 2 of a particular substance and I only have 1 in the reaction, if I multiply the reaction by 2, I multiply all the coefficients by 2, right? And that means I also multiply the enthalpy released of the reaction by 2. That makes sense? And then lastly, you add the reactions in order to get the delta H's, and make sure you always also add the delta H's. Don't do anything weird like forget about one. That'll make you look kind of silly. And we don't want to look silly. Right? Okay. So we're trying to calculate the overall delta H of this reaction, right? Given the following, you have the following thermochemical equations. I'm not going to read them all out because like you don't want to hear me see like C2H2. You can read it. And then, but remember that each one has its own delta H, and then remember what we're doing. So how are we going to go about this? Someone tell me the first thing that you would do when you see this. Mine is like cry, because we're not going to do that, because we know what we're doing now, because you went to 5able. My God, W plug. Look for the compound that's only in one equation. Okay, yeah, I like the idea. Yeah, I like that idea, Sophie. I get Sophia. Sorry, I almost called you Sophie. That's my bad. But yeah, I like that idea as well. The first one flips. It does. It does. Why does it flip? Why? Yes, exactly. Because you recognize the products in the reactants. Exactly. And you want C2H2 as a product, right? Because it's a product in this particular equation. Right. There you go. Look at you guys go. Okay. So the steps, like a lot of you said, reverse the first reaction and then multiply the second reaction by 2, and then you can sum. So why do we do it? I'm going to talk you through it a little bit slowly because yes, it is a lot. You did kind of manipulate a handful of things. But why? Right? So the reason we flip the first reaction is, like I just said, is because you see C2H2. However, it's a reactant. And that's kind of awkward because it's a product in our equation. We want it to be a product, right? So we flip the reaction. Now, what happens to delta H when we flip the reaction? What do we do to delta H? What changes? Does it change? Does it not? What do we do? Someone tell me. Yes, change the sign. Exactly. Don't forget to flip the sign. You flip the equation, you flip the sign. Perfect. There you go. Good. Yeah. So you change the sign. Okay. And then we have the second equation. We have carbon, the solid carbon, plus oxygen gas yields carbon dioxide, right? And that's fine. That's really convenient because it already has the carbon in the same position as we do. It's a reactant, and that's good. Lovely. However, it's a little awkward because we have 2 carbon solids. So what do? We multiply the whole thing by 2. So we have 2 carbon solids. But remember, we don't just multiply the carbon. We multiply both. We have 2 carbon solids. We also have 2 O2s now. And that means we end with 2 CO2s. So what do we do with delta H? We multiply by 2. Exactly. Yes, Nikhil. We multiply by 2. So we multiplied that negative 393.5 by 2. Got negative 747? No, 787. That's a plane. 747. I don't know. 787 might be. Anyway, so now you have all your equations, right? You have your equations lined up. Oh my gosh, hello. Oh yeah, so now you have your equations lined up. So now we can add down, right? And what happens when we add down? Things cancel. And that's really important, right? Remember, this is a good way to check your work while you're doing the problem. It's cool that it looks right. And it's like, oh yeah, this looks right. So let's do it. That's cool. But check your work. Because we all check our work here. Because that's how you catch your mistakes. That makes you a cool kid. Okay, I'm sorry. But anyway, so when we add down, we cancel things, right? So 2 CO2s are in the reactants and 2 CO2s are in the products of the first and second equation respectively, right? So what happens? They cancel. That's good. What else cancels? The H2O is a reactant in the initial equation and it's a product in the very last equation. That also cancels. Does C2H2 cancel? No. We don't see it anywhere else, right? But then things that not only cancel, they also add together, right? So if we have 2 O2s, that's also 4 over 2, same thing. So we have 2 O2s in the second equation, and we have half an O2. So if we add down, we yield 5/2 O2s. Typically, we don't. Typically, I know like when we have a standard reaction, you never really have a fraction as a coefficient. That's kind of awkward. However, when you're adding in this case, it's fine too. Okay, that's fine. But I will say this: if you are someone that recognized the fraction and instantly like multiplied the entire equation to get rid of the fraction, that's okay as long as you're consistent, right? And the reason that's okay is because you also have to multiply delta H. If I took this last reaction and went, oh my God, it has a half O2. That's weird. I don't like that. And I multiply by 2 and I got 2H2 plus 1 O2 yields 2 H2Os. As long as I multiply delta H by 2 and I keep everything else consistent and make sure everything fully does cancel, not just appears on both sides, but cancels equal amounts, you will still get the same result. Because you'll be multiplying everything as much, like you'll be multiplying everything by the same amount, and therefore you're kind of negating that work. Does that make sense? So don't be afraid that it's like, oh, like something's like weird, something's wrong. There's a lot of ways to get to the same result. Like that's like my like end point, right? Like that's my little like, I don't know, Aesop fable moral of the story moment. Call me Confucius. You know what I'm saying? So those cancel, which is good because we have 5/2 O2s as a product on the first reaction. And then overall, we have 5/2 O2s as the reactants in questions 2 and in reaction, 2 and 3. Right? So they cancel. Okay, so that means what happened? Now we add completely down, right? We have 2. Now what didn't cancel? 2 carbon, solid, 1 H2 gas, and that's all for the reactant side. And on the product side, we have 1 C2H2 gas and nothing else, right? And is that the same as our initial equation? Yes. Yes, it is. So what does that mean? That means we're chilling as a certified right guarantee. Sorry, I have these little bits that I keep repeating, but they're kind of dumb, but it's fine. Maybe you guys think I'm funny. But yeah, so that means we're cool, and that means we can add the delta H's down as well, and we can get a result, right? So we add down. We have plus, what is that? 1299.5 kilojoules, right? And then minus 787 kilojoules, minus 285.8 kilojoules. If any of you say no, I'm banning you. You know I have that ability, right? Okay. You're out. Just saying. Anyway, yeah. So what does that result in? That results in a delta H of plus 226.7 kilojoules. Okay. Get it? Got it good? Get it? Got it good. So let's recap. What are the different ways that we can find delta H? You guys know the names. I just went over the names. Put the names in the chat. What are the different ways? Give me some. What are the different ways to find delta H? Let me hear it. Yes. Hess's law. Heat of formations. Bond disassociations. Oh my God, look at you guys. Look at you guys. Look at you guys. Yes, exactly. So those are our 3 ways, okay? We have standard change. Standard change is what we were talking about with heat of formations, right? That's where our delta H of the reaction is equal to the sum of the delta H of the products times how much we have. That's our N. That's our moles. That's our coefficients. Minus the sum of the delta H of the reactions times the M, which is the same thing as N. It's just a different letter because if we use the same letter, people get confused. So remember, N and M are the coefficients. I saw that question like maybe a lot of times. So yeah. In this case, would you still be able to multiply the last reaction by 2, even though there would still be H2O left over? Is that, yeah, so like when I said, okay, I'll talk about this. Thank you. Thank you for yelling at me to look at my screen. Sometimes I'm like in the zone, like auto zone, you know what I'm saying? So if you multiply the last one by 2, right, you'd get 2H2 plus 1O2 yields 2H2O. Now that's cool, that's great. If you also multiply delta H by 2, that's fine, that's not wrong. However, when you go to cancel, you'll notice that in the first reaction, you have one H2O, and in the last reaction, you'll have two. Well, because you multiplied it by 2, right? That's weird because that doesn't cancel. Now you're left with 1. That's not okay. So in turn, then in that case, we would have to multiply the top reaction by 2. And if we did that, then we'd have 4 CO2. And if we have 4 CO2 and the second reaction also has 2 CO2, what happens? We have to multiply the second one by 2. So now what did we all do? We multiplied every single one. We multiplied the first reaction and the second reaction and the third reaction by 2 again. And what does that mean? It still means you'll get the same result. You will still get 226.7. And that's fine. Because the difference will still be the same because you multiplied everything by 2. But what you did is essentially irrelevant, is what I'm going to say. It's not wrong. You'll get the correct result, but it's unnecessary in order to get the result. Yeah, Anuva's a teacher. You know, Anuva was actually my AP Chem teacher in high school. She's like 44. She's like 44 years old. She like teaches at my high school. Yeah. Okay, so to recap, you guys talked about standard change. I also just talked about standard change. The second one is bond enthalpies. Like you said, bond dissociation. That was one of the things that you also said. Bond enthalpies are delta H of the reaction is equal to the sum of the delta H of the broken bonds minus the sum of the delta H of the formed bonds. Remember all of these, she doesn't look a day. Oh, yeah, you're right. She doesn't look a day over 30. Good for her, right? Anyway, but yeah, so remember the order is really important. The order is really important. And that's important because otherwise you'll get the wrong sign. And that's not good. You want the right sign because then you'll miss like the exothermic and endothermic. I'm 20. I'm not a boomer. I'm 20. To clear the air. I am 20, yeah. Okay. Enthalpies of formation. That was another one that you guys mentioned, which is great. Enthalpies of formation are the sum of the formation of the products times the amount of moles for the products minus the enthalpies of the reactants times the amount of moles of the products. N and M are the moles. Could you also divide the H if you divided the moles? Yes, you can. However, you get a little bit messy. You can do whatever. As long as you're consistent, yes, you can. However, I will say that you'll have to multiply much more often than you will have to divide. I don't know if I've ever had to divide, but that's cool. So if as long as you divide the H, that's cool. That's okay. Bond enthalpies. Yeah, the broken reactions. Yes. Essentially, yes. However, I would remind, like, as opposed to like broken bonds, for like AP Chem, like, yes, that's cool. If you go do chemistry, like, past AP Chem, then you're going to realize that's not exactly true. But in the end, like, yes, I guess for like your purposes of understanding right now, the reactants, like the bonds broken effectively that are the reactants, like, yes, that it would be first. Yeah. Okay, and then the last one that we just did, the one that you loved so much, Hess's law. Hess's law just means we manipulate the reaction. We manipulate subreactions, and we can use the sum of their delta H's, and we can add down or subtract depending on the sign, and we can find the overall delta H of the reactions. You guys are saying some crazy stuff. Oh my God. How is being 21 foot in the grave? 1 foot in the grave? I can't even have a sip of wine, bro. What do you mean? Anyway. We did already do this question, so I'm going to skip this multiple choice question. Just FYI. That was a fake samosa, and I apologize. But we're going to do this one. So that's fine. Yeah. Okay. So I'm going to give you guys a couple minutes. There's not like a timer on the screen right now, but that's fine. Because there's a timer in my heart. It's weird. But yeah, so based on these models, look at the models off the side. Which of the following accurately compares the energy changes associated with each of the phase changes? I will say, please don't put your answer in the chat until I let you. Please. I'm going to say that like 4 times, but please don't put the answer in the chat until I let you. Okay? Samosa fake returned. I'm not going to lie. Samosa totally fake returned. But she will actually return later. I don't know. There's Carnival of Body. My God. Look at Shazam over here. Jesus. Okay. You can put your answers in now. Your real answers. Your real answers. Give me your real answers. Stop saying D, please. Yeah, Nova did get an 870. That's actually her SAT score. Little known fact. That's not our answer to this question. So, good job. I just want to say, I'm really proud of you. Yeah. See? Yeah, well, let's see. Amazing pun. I'm so cool. Yes, it is C. Yes. The amount of energy absorbed by 1 mole of water molecules as they escape the liquid is equal to the amount of energy released by 1 mole of water molecules as they come together to form a liquid. Enthalpies of like formation stuff, enthalpies do go both ways. They do. And that's important to know, right? These things are equivalent going both ways. So the enthalpy of any given, like the amount of energy that is absorbed by 1 mole of water molecule as they escape the liquid will be the amount of energy released. However, notice that absorbed and released are important, which means the signs of the delta H's will be different. You guys need to get a hold of yourself like real bad. Okay, does that make sense? Are you good? Guys, guess what? I get the yap. 10-minute break. Go get some food. Go get some water. Go to the bathroom if you need to. And I'm going to talk. It's cranberry juice. It's cranberry juice. Right, yap time. Woo. It's cranberry juice. Can we stop with like the TikTok parties? I'm too old for that. It's cranberry juice. Can we stop asking me these questions? I don't even know what that means. What do you guys want me to talk about? Drake or Kendrick? In music or like the diss track stuff? Because the diss track stuff, Kendrick, but like in actual music, I definitely listen to more Drake by like a lot. Because I like melodic rap a lot. So, you know, it's like chill. Do I know what I want to specialize in after med school? A little bit, but not really. But also, I can't say it because you guys like, well, who was it? Someone was making fun of it a little while ago. So I can't tell you guys. So I'm not gonna tell you guys. So stop. I don't know what these words are. Are you guys even speaking English? Why am I so old? I'm not okay. Not doing dermatology. It's what I want to do. I decide in. I'll know what I am doing in 3.5 years. So like, ask me then. You won't know me then, because you don't know me outside of this. But like, you can ask me then, and if you ask, I'll answer. No, I don't know who. Hatsune Miku. I don't even know what that is. I don't know what that is. I do like Hours in Silence. It's okay. I'm basic though. My favorite Drake song is Passion Fruit. So, where can I ask you? Don't stalk me. That's weird. Don't do that. Passion Fruit is basic, but it's good. What do you want me to say? What do you want me to say? It's good. If you say you don't like it, you're wrong. Like, I don't know. That's it. Yeah, it's basic because it's good. That's what I'm saying. I don't listen to Kendrick. I don't listen to Kendrick. That's what I'm saying. I don't listen to Kendrick. What does that mean? What do these words mean? What do these words mean? PJ from AP. What does that even mean? Oh, is he another? No. Is he another person that I should know? I don't know people. Why am I a boomer? Okay. I'm 20 years old. So I'll have you know that I'm not. You're what, like 16? I'm like 4 years older than you. Can't be that bad. Surely. My opinions on the Kanye West comeback are also a little bit like I don't listen to Kanye either, like at all. I have listened to tech. I do listen to a lot of tech actually. I do. Exactly. You guys are just asking me these questions about these things that don't know about. You understand you're wasting your time. You're ruining my rap sesh. Yeah, no, I'm not freestyling. Yap sesh. I don't listen to Cardi. I give Pudgy. Don't. Why would you say that? Why would you say that? I do listen to Leve. I do listen to Leve. I do listen to say that Leve. Can I ban Sophia? Can we vote? You want to poll? Can we ban Sophia? Yes or no? I like Metro. I like Metro. I listen to Leve. Sumi. It's good. I did play sport. I was a swimmer. I swam in high school for not that long because I was in high school pandemic, so they didn't let us swim. But yeah. I don't know what happened to the smiley face. It still says I have the smiley face on Crowdcast, but no, I couldn't swim anymore because of a global pandemic. Anuva's making fun of people dying. Anuva's making fun of people dying. Said what I said. Said what I said. Okay, is rock climbing a real sport? Because I don't think so. I don't think so. It's not a real sport. Yeah, Anuva, but you need to be good to be in the Olympics. And also, like the speed thing, like, yeah, sure, I can get. Like racing, that's cool. But like just casual rock climbing, because I know Anuva didn't time herself going up that rock wall. I know she wasn't trying to go fast. You're just trying to make it up. Did you actually? Oh my god. Never mind. My bad. My high school GPA, I'm not telling you. I'm not telling you. I'll tell you my college GPA. I didn't do Model UN. I didn't do DECA. I did do Science Olympiad though. I did also do HOSA. My favorite boba flavor. Okay, you guys are gonna get mad. Okay, but I only like popping boba. I don't like the tapioca pearls because I don't know. To me, not okay. But I popping boba is really good. I like the passion fruit popping boba, dude. It's so. What do you mean nobody cares? Someone asked me. It's good. The tapioca ones like feel like I don't know. They make me uncomfortable. They make me uncomfortable, and it's not that good. But like, so I'll get it with like a fruit tea typically. So I'll get like a passion fruit popping boba with like peach green tea or something like that. You know what I'm saying? Tapioca is exactly. Tapioca is overrated. Tapioca is overrated. I am a Costco guy. What are you gonna? I am. And what about it? Costco's good. I literally just I went today. I was there today. I was there literally 3 hours ago. And what about it? Spent like $300. You know what I recommend for MCAT prep? I recommend you stop thinking about it when you're like 17 and think about it when it happens. But also, I hated you world. So that's my answer. I did use Kaplan. But also, stop thinking about the like. Stop. You're like not old enough. Don't live your life. Live your life. I said this yesterday. Someone asked me for cars tips yesterday. I was like, what? No. I'm not from Houston. I'm from Chicago. Yeah, Nova, join the stage. I have a friend. Do you want to yap together? Actually, no. You're just gonna yell at me or something. I don't know. There you are. Hey.
Oh my God. I'm just gonna drop the boba flavor, mango green tea, 50% sugar, less ice with regular boba.
I get
Anyways.
125% sugar. I like it sweet.
Oh my God.
I like it sweet. What did I get on my SAT? Like a 15,980, 1580. Anyway,
He needs the Botox,
guess what?
by the way.
Okay, can we not? Can we not? You shouldn't MCAT prep for freshman year ever, because don't do that. You MCAT prep when you schedule your MCAT 6 months out, and then you start MCAT prepping. As a freshman, and you just do clubs, live school, have a good life, have fun, do well in your classes. That's all. Okay, break over. You know what that means? You guys are done with me. I'm gone. This is not a guess Raki's age because I said my age so many times. But you know what that means? Yash is here, and I'm gone. So I will see you guys later. I'll be back, like maybe at the end. Maybe. I don't know. Or maybe I won't be because maybe I'm not happy. I don't know. Bye-bye.
Hey guys, what's up? I think Rahi's coming back though, so like he's not gone for the night. I think he has the last few slides. So let's get started. All right. The first thing we're doing is actually playing the quiz. So join in. Oh, he's coming back. He's still here. Thank you. Scan the QR code. I can drop the link in the chat in a second. And yeah, we will be having the music today. I will be able to stream the music, thankfully. Here's the link. Just right before the chem exam, make sure you've had lunch. It can go. It's the first AP exam of the day, so it's usually going to go pretty late into the day. Maybe it's 5 o'clock, 4:30. Also, make sure you read every problem fully. There's like a lot of tricks. They try to trick you up on a lot of different things. No, I mean we're doing all the content prep here, so we should go over the non-content stuff. My routine. I wake up in the morning. It's in the afternoon. MCQ tips. If you can't get it in like a minute, guess on it. Let me stream the actual quiz out now. Tell me if you guys can hear. Yeah, I'd go first last year. So bad. 7 to 10. Try not to overuse your calculator during the MCQ. I feel like okay, sorry. Lower the volume? Okay. Is that better? Anyways, get your answers in. We gotta do the equilibrium section next. It's a big section. How do I join? Just click this line. These are a little bit harder, yeah. Yep, either one works. The answer to this question should be B. So I'm not sure again why this question has it listed as A. I don't understand why it's listed as A, but it should be B because delta H is not reliant on pressure. Remember that delta H is at constant pressure, and so there's no conclusion that you can make. The reason A is incorrect is that if you have a different number of gas molecules, it doesn't necessarily influence the delta H. For delta H to be approximately 0, that's a very rare situation in the first place, and the rest of it is also not correct. And D is just the inverse of B, and since A completely makes no sense, D also completely makes no sense. What is this? Is there something wrong with how it looks, Anuva? It's cropped. Okay, better now? Do I zoom in? You guys want me to zoom in a little bit more? Can I explain that a tiny bit more? Delta H has no influence, is not influenced at all by the number of gases in the system. That's more a delta S thing. Zoom in. Okay, I'll zoom in a little bit. Is this better? Adam, just let me know, or anyone else too. Okay, this seems to be good for everyone. So B is right. Yeah, B would be right in that situation. We didn't talk about delta S today, so I'm just gonna, well, we can answer this question, but yeah, you guys seem to have mostly gotten it right. That's great that you guys still remember delta S. I don't know why this was delta S question. Again, I think the quizzes are a little bit whack. Okay. Let's skip this. Oh, this is because it's a unit 6 one. Hold on. This is a unit 6 one. Does anyone have a unit 5 link? This is a unit 6 quiz. The unit 5 link doesn't work. Yeah, this is. Oh, we did just do unit 6? Okay. Okay, never mind. We can continue with this. It feels like a lot more equilibrium here. But yeah, this is a Alicia question. So if you guys want to continue answering this, yesterday, yeah, sorry, that's my bad. That's my bad. Yep. So in an endothermic reaction, you have to add heat to make this reaction go forward. You can think of heat as like a pseudo-reactant. And so when you're increasing temperature, you're essentially adding heat, and that would push the reaction forward towards the product side, similarly to how you would be adding a reactant, similar to what would happen if you add a reactant. AP senioritis, yeah. It's gonna be next year. TQD. What does that mean? What does TQD mean? Does Fiveable have AP MCQ practice or just a general MCQ practice? I think it has a huge bank of just general MCQ practice. Some of the concepts are almost identical to what you'll see on the AP exam. They're just not formatted the exact same. But yeah, Fiveable's question bank is pretty. Turkish consulting. Yeah, I'm still a high schooler. I forget which one did we make Rahi? Did we make Rahi Blue Tie Kid, or did we make him Turkish one? Wow, everyone got this one right. Exactly. Yes, this is just Hess's law. You flip the equation, and you get it. You reverse the enthalpy change. Yeah, I took it as sophomore in 5. Yeah. This is a Unit 9 question, but I'm 17. This is a Unit 9 question, but we will still do it, and we'll see how you guys do. Your teacher didn't get to Unit 9? It's okay, we'll get to Unit 9 tomorrow. Don't worry. So just come back tomorrow. I'm a junior, so I'll apply next year. That is me. Yeah, that is me. I don't know yet. It's still a long time away. It's a long time away, a whole summer. All right. Wow, looks like you guys did really well on this one. Yeah, so remember, for a reaction to be spontaneous, it has to have negative delta G. And delta G, I'll put in the chat, but delta G equals delta H minus temperature times delta S, right? So if you had high temperature, wait, let's say that's an increase in entropy. Let's just say that's an increase in entropy for the purpose of the question. If you have an increase in entropy, delta S is positive. And so in that situation, your dH, which is a positive number, would be outweighed by a super high temperature times a positive delta S. Because that would be a negative number, right? Because you have a positive number minus a negative number, and you increase that negative number, it's going to become a negative. The whole sum is going to become negative. And when it is negative, delta G will be equal to less than 0, which will mean the reaction is spontaneous. I'm 06. Yeah, let's focus on the chemistry. That was just like an end of screen. Question 5. Question 5. It's all right. Let's not dive too deep into question 5. If you come back tomorrow night, we'll spend a lot of time going over Gibbs free energy, entropy, and what it means to be for a reaction to be spontaneous or thermodynamically favorable. That's how he likes to phrase it these days. Yeah, these are a lot of words. I wonder who wrote this. Was this written by Chat? All right, great. You guys seem to have done well on this one. So remember that we have been talking about thermodynamics all of tonight, right? So thermodynamics will tell you if a process is thermodynamically favorable, but it won't tell you whether it's kinetically favorable. Kinetically favorable means that the process actually happens. Thermodynamically favorable means that if it does happen, it would be favorable. It would be good. But remember, kinetics is how fast something happens. For example, like hydrogen-oxygen combining, like the equation in chat, 2H2 plus O2 going to 2H2O, is thermodynamically very favorable, right? But if you mix gaseous samples of hydrogen and oxygen, they're not going to ignite and turn into water unless you give some energy to them in the form of a spark, because the activation energy to react is very high for this reaction. So just because something is thermodynamically favorable doesn't mean that it happens super fast. How fast a reaction happens or its rate is influenced solely by its activation energy. Okay, this question is basically saying that two reactions have the same thermodynamic quantities, as in their delta H is the same exact. So like on the curve, the energy curve, they both start and end at like the same difference between them, like the starting and the ending, but their rates are different. That just means the activation energy, or like the point at where you have the activated complex, is a different distance from the reactants, if that makes sense. Does that explanation help you guys? You can immediately eliminate A. You can it's basically saying a whole lot of nothing. C, there was nothing. We never even brought up a catalyst in the question. And D, you don't even learn what a hydrolysis is, at least not to my knowledge, in AP Chem. So you wouldn't be selecting D. If you can recognize all the words in B, it's probably going to be right. I'm going to skip this. This is a pretty deep thermodynamics question, or Unit 9 question. This question is a little strange. We'll see. Okay. Let's imagine it said solid transforms directly into a gas without becoming a liquid first. Yeah, it is. It is. You're right. I don't know the questions. I don't know how they're made exactly. It's just compiled by unit. I'm not sure how the questions are made. Okay, this is our last question, guys. And instead of note that in this question, this is a kilojoules per mole. When it says heat of fusion in joules per mole, it's asking really kilojoules. Or, if you get an answer in joules converted to kilojoules, you should get the right answer. Remember, when you're ever confused, dimensional analysis is always helpful. Can we go over this question? Yes, we will go over this question when we see the answer. All right, seems like less than half of us got this question right, so let's take some more time to go through it. So heat of fusion is, again, the heat it takes to melt, go from solid to liquid, right? We have one more unit left. Heat of fusion is the heat it takes from going to solid to liquid. So immediately, the heat of vaporization is extraneous info. We can just strike that out on a piece of paper, cross that out. We don't need that, right? So we know that the heat of fusion is 334 joules per gram. And the question is asking us, what is the heat of fusion in joules per mole, right? And we know that in 1 mole of water, there are 18.012 or 016 grams of water. Remember, that's just from molar mass, right? 18.016 grams per mole. That's the molar mass of water. So we can eliminate, right? Do dimensional analysis. Joules times gram, 334 joules times gram times 18.016 grams per mole to get our units of joules per mole of 6,000. And the question, as I specified earlier, is actually kilojoules per mole. And that's how we get to 6.01. Does that make sense? D is incorrect because that is, again, the joules per gram. This is a common trick they'll have you do, joules per gram versus joules per mole. You don't need to use vaporization because the question is just asking about fusion. Yeah, it's just extra information. They're trying to trip you up. 41 is actually the roughly the heat of vaporization in kilojoules per mole for water. So no one really picked A, but still. And B, I'm not sure what B, how we get to B. Yeah. All right, are we good? Why do you multiply by 8.02? Because you want to get joules over mole, right? And you have 18.012 grams over mole. And you want to cancel those grams. Grams in the denominator here, grams in the numerator here. All right. I think we're good on this. Let me move on to the slideshow, and we'll get started on Unit 7, Equilibrium. All right. Yep, exactly, Melody. Wait, but when you multiply by, it is 334, not 1334. That might be your mistake. equilibrium. Yep. All right, let's get started. All right, we got to pick up our pace a little bit because, yeah, we are running out of time. All right, so equilibrium is like roughly 10% of your exam, and there are a lot of different concepts in it, but really these are going to be free points. So let's go ahead and look at it. So before we get started, we have to really define what equilibrium is. Equilibrium is just a point at which there is no net change in the concentration of products and reactants. This doesn't mean that the reaction is still not occurring, right? This means that the concentration of the reactants and the products are not changing. AP Chem calls this dynamic equilibrium, which is really the point at which these concentrations are becoming constant, and even though the rate of the reactions are still positive, non-negative values, right? So here's a quick graph. Say you start with a system where there's only reactants, right? And we're looking at a graph where we have time on the x-axis, reaction rate on the y-axis. If you only have reactants, you're only going to start with some forward reaction rate, right? And this forward reaction rate is slowly going to decrease and decrease as more of those reactants are converted into products. And as you get products, some of those products will react to form reactants, go backwards. So the reverse reaction rate will also increase. And then eventually, these reaction rates will come to a point where they meet, and at the point where they meet and become the same exact value, you will reach equilibrium. Now remember, at equilibrium, reaction is still happening. It's just there's no net change. There'll definitely be one MCQ about that. All right, so when you want to figure out the direction of your reversible reactions, you want to use these two different values, K and Q. So K is basically a way to measure the relative concentration of all the species in a reaction at equilibrium. So the important note about K is that it's at equilibrium. You already know, probably from the law of mass action, that K is really just equal to the concentration of a product times to the raised to the power of its coefficient in the reaction equation. That's just the general statement of the law of mass action. So K is really just your equilibrium position. When at every time you're not at equilibrium, you're working with Q. So Q is your not equilibrium. If you're an inch off equilibrium or you're a mile off equilibrium, you're still working with Q. Q is calculated the exact same value in the exact same way as K, except the value will be different. And the relative value of Q to K influences the way the reaction will occur moving forward. So if Q is greater than K, remember we have products over reactants, right? So if Q is greater than K, that means we have too many reactants or too many products, right? We are top heavy. We have too many products, right? So that means we're going to see a shift back. Yeah, C and D is product. Yeah, we're going to see a shift back towards reactants to even it out and get back to K, right? If Q equals K, obviously we're at equilibrium, right? Because K is the value of the relative concentration of the species at equilibrium. Now, conversely, if Q is less than K, that means we are bottom heavy, right? We are too much on the bottom, decreasing the value of Q, right? And so that means that we'll have to shift towards the products to make it balance. So if Q is less than K, we shift towards products. The exponents are coefficients of the reaction, yes. You only solve for Q when you're given all the concentrations, right? Yes, if they give you Q, the value of Q, they can be asked to algebraically manipulate it and solve for a concentration too. C and D are products, A and B are reactants. All right, one important note with Q and K is that QC and KC are not always the same thing as KP and QP. KC and QC refer to concentration, so molar concentration, while KP and QP refer to pressures. So KP and QP are technically the right K values. They're the thermodynamically correct K values. But oftentimes you'll see KC and QC. But usually you just want to use what they give you and don't overcomplicate it too much. All right, so here are some things you can identify when you know the magnitude of your equilibrium constant. So if you know that your K is very, very much smaller than 1, the reaction barely occurs, right? If K is much, much smaller than 1, you have very small P, and you have a very large R. Small amount of products, large amount of reactants. Your reaction can barely occur. Similarly, if you have a K that is slightly smaller than 1, you have a small amount of P. You have a relatively large amount of R, not a very large amount of R. And in both cases, you know that reactants are favored. The exact opposite, if K is greater than 1, or K is much, much greater than 1, you have more products than reactants, right? The larger the K, the more products you have. If K is greater than 1, you'll always be product favored. Okay. I think I have to refresh that. I'm going to refresh my slides 1 second. Are the animations good now? Yeah, okay. Remember that K cannot be a negative number. K always has to be positive. It just depends on whether it's greater than 1 or less than 1. All right. So, as Rahi covered Hess's law, some of you guys were talking in the chat about how this applies to equilibrium too, right? So if you reverse the reaction, in Hess's law, you flip the sign, right? But in equilibrium, you flip the value of the actual thing. So you put the whole K value over 1. You take the reciprocal. If you multiply it in Hess's law, you just multiply the enthalpy value, right? In this case, instead of multiplying, you raise the whole K value to that exponent, and to the exponent of the factor that you multiplied. In Hess's law, when you combine reactions, you just add the enthalpy values. In equilibrium, you multiply them. All right. So this is an important concept in chemistry, the ice table. The ice table is basically just another way to state the law of conservation of mass, right? If you lose something, you have to gain something. Yes, ice tables are very important, especially for the FRQ. So when you're drawing an ice table, you want to have the reaction, of course. I've seen it referred to as a rice table before, reaction, ice. But really, you just want to write the reaction out. You want to write the initial concentration. You write the initial concentrations of all the species as you know. Then you write the change. So what changes? And then you write the equilibrium concentrations, or like the final concentrations, once everything has evened out and equilibrium has been established. So let's work on a slightly harder example. All right. So in this case, we have to determine Kc for the following reaction. That's important. We can't just use pressure or moles. We have to convert to molarity. All right, so remember that. Somebody did it. Okay, whatever. All right. All right. So we are at the reaction, right? We have 2x plus goes to 3y and 4z, right? We know that we initially had 0.5 mole of x, and at the equilibrium position, we had 0.35 mole of x, right? We know that since the coefficient on x is 2, the change in x was negative 2x, right? So we know that our final, right, equals 0.35 equals 0.5 minus 2x. Doing the algebra on that, we can see that x is equal to 0.075 mole, right? And now, knowing that we gained 3x y and 4x z, right? We know that our final concentration of y is 3x, which is 3 times 0.075, which is 0.225 molar. And we know our final concentration of z is 4 times little x, which is 4 times 0.075, which is 0.3 molar, or 0.3 mole. You can tell when x is negligible when k is much, much smaller than 1, or k is much, much greater than 1. Can you explain why you like multiply and do like 3x and 4x instead of doing 3y over 2 divided by 4? I'm not sure. I think you might think wrong. Someone in chat can answer that question. We should convert mole similarity. Exactly. That's exactly where I was going. So we know that Kc is equal to the molar concentration of y cubed, because of the coefficient of 3, times the molar concentration of z to the 4th, divided by the molar concentration of x to the squared, right? And now we know that the molar concentration of y, for example, is moles over liter. The moles of y is 0.225. The liters of the whole system, remember, look at the initial problem. It's at the end of the first sentence. The liters of the system is 0.75 liters, right? So you have to divide 0.225 divided by 0.75 to get our molar concentration of 0.300. Similarly, to find molar concentration of Z, we take our Z, number of moles of Z, 0.3, and divide it by our liters, which is 0.75, to get 0.4, right? And then we take our moles of X, and we divide it by our liters of system, which is 0.35 divided by 0.75, which equals 0.467. We square the number. Now, taking that whole product, we get that the equilibrium concentration is, the equilibrium constant is 3.17 times 10 to the negative 3. That should be times 10 to the negative 3. I'm not sure why. That's not, but that should be 10 times 10 to the 3. So, sorry about that. I think I edited this slideshow. I'm not sure why it all reverted back. Okay. Yeah, all right, cool. Let's do some questions on that, because I think this is a hard concept for us to understand. If you don't use the 5% rule, the 5% rule, just stick to applying it only in acid base and solubility calculation generally for now. More questions? Okay, I think you guys understand this. I will be moving on. If so, I just want to really make sure you guys have a strong foundation in this, because this will show up on your exam, at least at some point. When do we multiply k's? K's are just multiplied when you have, again, when you're summing equations like this, all the way to the right. Will E for the reactant be given in FRQ? It depends. They might give you the equilibrium concentration for a product, and you can find X that way. All right, let's move on. All right, so there will be lots of pictures and diagrams of chemical equilibrium, and you'll have to kind of interpret them. Particle diagrams are especially common in AP chemistry. So here's an example. We have a system of N2O4 initially, right? At T equals 0, we have all N2O4. And we are seeing this react to form both, to form 2 molecules of NO2 per each molecule of N2O4, right? So the question in this situation might be, at what time do we have equilibrium be established in the system, right? So going back to our definition of equilibrium, equilibrium is just established whenever we have concentrations that remain constant. So if we count it up, our T equals 40 seconds, our T equals 60 seconds, and our T equals 80 seconds all have the same concentrations of both N2O4 and NO2. Namely, we have 5 particles of N2O4 and 6 particles of NO2. Since these concentrations remain constant, we know that equilibrium has to be established before 40 seconds. Since the concentrations are different, we have 4 blue particles, meaning 4 NO2 particles, and 6 N2O4 particles. We know that the concentrations are not at equilibrium, right? So in this time period between 20 and 40 seconds, equilibrium has to be established. All right, this is another common example we'll see, but I think, let me move on. Let's first go over Le Chatelier's principle. So Le Chatelier's principle basically just explains what happens when a stressor is added to the system. All right. So if a stressor is added to the system, a chemical reaction will always shift in the direction that minimizes that stress, that makes it so the stress isn't felt as much. So, for example, if you have a system where your reactants go into products, right, and you add a bunch of reactant, the system will shift towards products using up those reactants, and therefore kind of mitigating the stress that the additional reactants place on the system. Right? So you can use the Chatelier's principle for concentration, temperature, and pressure. Yeah, we'll be going through lots of examples of how this works in the next slide. But one super important note. Super important note. This will be a question on your AP exam. Half of you guys will probably get this wrong. Catalysts do not in any way affect the rate of reaction. They do not induce any stress in the system. They simply catalysts only affect the rate of reaction. They do not affect the position of the equilibrium at all. In no way do they affect the position of the equilibrium. So you might see a question, pretty common question is like, how do we increase the yield of this reaction? How do we make more products? You will not get this wrong. Yeah, if you're listening, you're not gonna get this wrong. You're not gonna get this wrong if you're listening. Catalysts will not increase the yield. They will not increase the products. They will only make the reaction occur faster. Okay. So let's do some examples. So if you have this reaction, 3H2 plus N2 is in equilibrium with 2NH3. If we decrease the concentration of N2, we decrease the concentration for reactant, right? So we decrease concentration for reactant, our reaction will shift back towards reactants, right, to make up for that. Let's do another one. If we have H2 plus I2 is in equilibrium with 2HI, that should be H2 and I2, and we change the container, what will happen? So in this situation, we have equal number of moles of gas, right? So we change the container. We will not be crumpling it. We will not be expanding it. There will be no pressure on the system. There'll be no pressure for the system to do anything. There's no change in this reaction because we have the same number of moles of gas on both sides, right? We looked at this extensively in the previews. Here we have a temperature situation, right? This is an exothermic reaction. That means you can think of heat as sort of a pseudo product, right? Heat is produced, right? So if we decrease the temperature, we're quote unquote decreasing a product, right? And in that case, we'll see the reaction shift towards the product side, favoring products, because you want to produce that heat, right? And here's a more complicated example. This is a classic, the process to make ammonia, classic reaction. Here we have N2 reacts with 3H2 to form 2NH3, right? And we have, on the very left side of the graph, we have a system where the system is at equilibrium. So that means all the concentrations are the same. Now, the first change we'll do to the system is we'll suddenly add a bunch of N2, right? And if we suddenly increase the amount of N2, that means we'll have a sudden increase in number of reactants, meaning there'll be a shift towards the products. In that case, you can see how NH3 slowly increases and N2 slowly decreases as it's used to consume NH3. And also, important to note, H2 actually decreases because as you see, the reaction shifts towards the right, using up H2. Now, here's another example. We change the pressure. Say we shrink the volume, therefore increasing the pressure of everything in the system, right? And now when we increase the pressure, we are constricting the system, right? We're constricting it. That means that our reaction is going to shift to the side with fewer moles of gas, all right? That makes sense conceptually if you think about it. If you squeeze something, it's going to want to become smaller. So it's going to shift into a smaller, I'm sorry, but how do you know whether it's a concentration, pressure, or temperature change? This graph tells you. They'll tell you also in the AP exam. All right, let me go back to where I was pressure change, right? Pressure change. You increase the pressure by shrinking the volume, right? And so the pressure of everything has increased, so the reaction will shift to the side that is fewer moles of gas, therefore becoming smaller and better able to fit in that higher pressure, smaller volume container. And in this reaction, we can see that we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. So we're going to see a shift towards products when we increase the pressure. In that case, we'll see an increase in our NH3. Hold on. All right, we'll see an increase in our NH3. I don't know what exactly is happening in this graph. Maybe this is referring to increase the pressure of. No, I don't know what they're doing, but just know that if you increase the pressure of NH3, or if you increase the pressure of the system, it'll shift towards NH3. Similarly, this reaction is exothermic. If you were to okay, wait, yeah, the NH3 is increasing. Yeah, sorry. NH3 is increasing similarly to what you would see the pressure increase. If you increase the temperature of this reaction is a little slightly exothermic reaction, right? And if you increase the temperature, that means you're kind of adding a pseudo product, right? This temperature is an exothermic reaction. This reaction is a exothermic reaction. So if you increase the I'm struggling. If you increase the heat added, right, you're kind of increasing a product. So you're going to see a shift back towards your products, right? Because you're kind of adding a reactant. You're kind of adding a product. And so you're going to see a shift towards reactants. Sorry, I was really stumbling over my words. All right, does that make sense? Does anyone want me to re-explain a concept here? Because I did not do an amazing job. Okay, wait. If it shift left, then why does NH3 also increase in exo? Okay, I need someone. Can someone frame a question? In exo, heat serves as a product, so we'll shift to consume the same product to decrease it, and as a result, the reactant will increase. That is correct. What does not affect equilibrium? Basically, everything affects equilibrium except for catalysts. Wait, but if it shifts left, then why does NH2 also increase? If it shifts left, NH3 should not increase. It should decrease. How do you know it's exo? I told you this. They'll tell you this too. All right, let's move on. All right. All right, solubility and precipitation equilibrium. So this is another big part of equilibrium. It's the solubility. So KSP is just your solubility constant, right? So for KSP calculations, you're never going to have a denominator, right? Because the denominator would be a solid, and the activity of a solid is just 1, right? So, Kinnick, are you taking over from this point onwards?
Yeah, I'm just here for moral support.
Okay, cool. So remember that KSP is just going to equal your products of your reactants. Your reactants in this case have an activity of 1, so it's just going to be the concentrations of your products. For NaCl, this would be Na times Cl. All right, there are no coefficients here. If we had coefficients, we would raise this to a certain power. Since your KSP is basically a measure of the concentration of your products, which are the dissolved ions, the higher the value of KSP, the more soluble your substance is. Now, here's an important effect that you'll have to know, is the common ion effect, right? The common ion effect is basically, it's best to do an example, right? So we have a solution of calcium nitrate, right? Calcium nitrate, we have calcium, a nitrate dissolves to form 1 calcium 2 plus and 2 nitrates, right? If we add some calcium just by itself in the form of maybe calcium chloride or calcium bromide to the solution, we will actually see a decrease in the solubility of calcium nitrate, right? Because what we'll be doing, in essence, is adding a product in the form of calcium 2 plus dissolved in water, which will be shifting the reaction left to form more of the precipitated calcium salt, the solid calcium salt, the undissolved calcium salt. This is basically just an application of Lechat. So that's common ion effect. When you see common ion effect, always think Lechat. Now, there is a strong pH dependence. pH can have a strong effect on your solubility. All right. So you guys already know how pH works. And if you increase your pH, you're just adding hydroxide. If you decrease your pH, you're adding hydronium or hydrogen ions, H+. In equilibrium, you kind of very briefly go over pH. For example, if you add this basic ammonia, NH3, you will produce OH minus, increasing your pH. Now, this is a Unit 9 concept, but it kind of ties into equilibrium. It's the free energy of dissolution. So equilibrium relates to dissolution, right? Equilibrium relates to delta G and not anything else. So delta G is calculated by taking delta H and subtracting it by T times delta S, right? This reaction will always occur if your delta G is less than 0. So for dissolution processes, you can justify a lot of things by examining the sign of delta H and delta S. Usually, when you dissolve something, something with strong big charges, when those big charges get solvated by water molecules, like a calcium 2 plus molecule is surrounded by OH2, the O side, the partial negative O side, you'll see a delta H less than 0 because heat is released when those IMFs are formed between those ion dipole IMFs are formed. But at the same time, you may also see a decrease in entropy because you have that very structured solvation layer around that strongly charged ion. It just depends really on whatever species you're working with. For example, ammonium nitrate, that has a positive enthalpy of formation because those charges are not very concentrated, they're not very strong. So when you dissolve it, there's not a high degree of solvation, and the delta H is actually greater than 0. But conversely, since there's not a high degree of solvation, the delta S is greater than 0. And at high temperature, the whole thing evens out to make delta G less than 0, and that makes it insoluble. So you often want to justify whether something is soluble or not by going back to this delta H minus delta T by minus T times delta S. All right, I'm going to skip this. We're going to go over this better tomorrow night in Unit 9. But let's do a quick practice problem. So let's start with question 1. How does changing the temperature affect the value of the equilibrium constant for an exothermic reaction? So let's put in the chat, guys. Now remember, in an exothermic reaction, you can kind of think of heat as a pseudo product. Change the temperature. Either way, like describe it. If you increase the temperature, what happens? If you decrease the temperature, what happens? So those of you just saying it decreases K or it increases K, be more specific. If you increase temperature, what happens? If you decrease temperature, what happens? All right. Yep, you guys are mostly getting it right. So if you increase temperature, you are decreasing K because you are kind of, as you remember, heat is a pseudo product. Right. And remember, the only things that actually affect the value of K, big K, the equilibrium K, is temperature. Nothing else. All right, let's do number 2 now. how the addition of a common ion to a saturated solution affects its solubility product constant. So, yeah, I'll wait for do a couple more times, guys. Let's put some answers in the chat. Temperature and K are not an inverse relationship. They're related based on the sign of delta H. So yeah, those of you guys saying it decreases solubility, that is correct. When you add that common ion, it does decrease solubility. However, it does not change KSP. KSP is only impacted by temperature, right? So it doesn't actually affect KSP. It just affects solubility. Does that make sense to you guys? KSP does not change. KSP is a constant value unless you change the temperature. The only way you can change K. Why does it decrease solubility? Because you're kind of adding a product, right? A product in that KSP expression. You're adding a product. That is basically the common ion effect is just Le Chat. All right. Are we doing this MCQ practice? Let's do this MCQ practice. So I'll give you until 9:18 to finish this up. I think Rahi is taking over after this MCQ question. Right, in 9:18, post your answers in the chat. You can't read the table. Basically, the pressure is just slowly increasing as time goes on. Yep. Let's see what you guys got in the chat. C. Okay. The answer is in fact C, right? Because the acetone is just slowly vaporizing, right? And then eventually, once it's vaporized enough, the rate of vaporization is going to be equal to the rate of the condensation, and your pressure is going to stay constant, right? A is incorrect because at some point the acetone pressure levels off at 130. You can see after 1 minute 30, 1 minute 50 sec, 1 minute 50, 1.5 minutes, the pressure is constant at 130 kilopascals. B is incorrect because not all of the acetone vaporizes, right? The question explicitly says some acetone liquid remains in the container. All right. C is correct because we just explained. And D is not correct. Remember, because we have dynamic equilibrium, which means that at equilibrium, even though the concentrations are no longer changing, the reaction is still occurring. The rate of the reaction is non-zero. All right. So there we go. And let's take a 5-minute break. I think it's next. It's just a 5-minute break. And Rahi will take over now. So let me end my stream. Yeah. Bye, guys. Thank you.
All right, I'm gonna give you guys like 5 minutes, and I'm gonna talk some more. I know, dude. I like come here just to yap, and then I leave. Like, what else is my job, dude? Yash is the actual content guy, I guess. I don't know. But after 5 minutes, and I guess the 30 seconds that I accidentally put on, we're gonna do a cram quiz, and we're gonna move to a little Q&A, and yeah. All right. Get it? Got it good? All right, talk to me about chem. We're gonna keep, okay, you know what? I'm gonna yap, yeah, because you know me, but I'm gonna yap about chem and not about other things because we already had that little happy fun time and we're done with that happy fun time now. Okay? For ice tables, when can we ignore numbers? I don't, okay, so I think what you generally mean with like ice tables is like when you're talking about like molarity versus like concentration and stuff like that, you can generally use the like either molarity or concentration as long as you're consistent. And then yes, when you are calculating some stuff like KSP, when when you're doing like a large number minus X, right? Like say you're doing like 0.3 moles or something like, or like even like 1 molar minus like some value X, and that X generally is likely to be negligible, you can ignore X because otherwise you're going to have to do things where you have like X in the numerator and denominator and stuff like that. And then you like, in order to solve for X, you'd have to do like the quadratic formula, which you are not expected to do on the AP exam, right? So when X is small and you're doing a large number minus X, X in that case is negligible. And generally you can just ignore that and have that number. And that way it'll make it easier to calculate for X such that you aren't, doing the quadratic formula or anything a little bit too like funky. If we increase or decrease, the temperature of a system at equilibrium, will it shift to the endothermic side or the exothermic side? So it depends on what you're doing with the heat, right? Like it depends on the system of the particular reaction, right? It depends on if a system is at equilibrium, right? You need to know what the delta H is. Is the delta H negative or is the delta H positive, right? And my favorite way to like think about delta H in that case is to think about it as either a product or a reactant. In an exothermic reaction, when delta H is negative, it will be on the product side of the equation. It's effectively just another thing, right? If you're reacting and you're making CO2, cool. Now you're making CO2 and also some kilojoules of heat, right? Also say like 400 kilojoules of heat per mole. So in that case, it depends on what you're doing, right? If you're injecting temperature, if you're injecting heat into a system, if you're injecting energy effectively into a system, right, and it's a product, what's going to be favored? Well, you're injecting more product, which means the reactants are going to be favored in a system at equilibrium. If it is an endothermic, however, if it's an endothermic reaction, heat is a reactant, right? Because you need heat and you're using up heat and you're not returning anything when you get to the product side, which means in that case, if you say inject heat or inject energy into the system, you are going to inject on the reactant side, and therefore in the system at equilibrium, you will favor the products. Does that make sense? It depends if the reaction is exothermic or endothermic. You can't, like, that is not like, you can't, so you're like, essentially, the way you're asking a question is like you're posing two different variables, right? But it can't be that. It's either going to be exothermic or endothermic. That is a given. And then if you change the temperature, either increase or decrease, it will, like, some change will occur based off of the equilibrium and based on whether it's exothermic, endothermic, and what side that means that, like, the heat is on effectively. Solids, yeah, solids do stay constant because they're a pure substance. Yep. KSP is molar solubility. So KSP is just a solubility constant. Every substance has a solubility constant. It describes more like how soluble it is and what that system means in equilibrium because of how soluble it is. Why would increasing temperature make K lower? Again, so when we're talking about Le Chatelier's principle, right? When we're talking about equilibrium constant. Yeah, that previous question was a very, very loaded question. That's a lot of chemistry that you don't need to know for the AP exam. Yeah, Yasha's right. I just want to reiterate that. I'll reiterate it out loud. K is a measure of relative activity, generally speaking, right? It's the reason like we call it like a particular constant is because of that. It's a relative activity for a given reaction and for a given system. Equilibrium, I would say, is generally an FRQ question, just because like it's a lot of like questions that you can like have like multi-part questions to. But like, so I would say like yes, it is generally an FRQ question, but I wouldn't like you're not going to see it in FRQs, but you'll see, or multiple choice rather. You will generally, you'll see something. Is KSP only affected by temperature, but K is affected by volume, pressure, and temperature? Yes. You have it, yeah. Exactly. Guys, we're almost done with our break. So sorry. How many questions will be lab-based, dude? I don't know. Okay. Guess what? Break's over. Sorry. College Board doesn't typically use last question. They have on rare occasion done it, but typically, like, even if they use a question, it's typically like an FRQ question where they change the numbers. So like, but multiple choice questions are reused. But when I say reused, it's typically not like a calculative question. On about 10 questions, I think on your exam are going to be experimental questions, the ones that are they're just like trying to, you know, like figure out and stuff like that. And then those can be like re-seen, like if they decided that it's a good question, they want to re-inject it. So they do stuff like that. But guess what? It's cram quiz time. So join. We're going to put the link in the chat. Someone's going to put the link in the chat, not me though. And then just join up and we're going to get started. I'll give you a couple seconds here and then I'm going to switch like to my actual quiz and then we'll go from there, okay? Perfect. The link's in the chat. The other one now. Oh, my face is so big. It scared me. Okay. Join. I'll give you guys like another minute to join. Am I reverent? Sure. Better question. What is reverent? So catalyst, okay, so yeah, quickly I'll answer this question while you guys are joining, right? The catalyst does not change so it does not change the equilibrium in the reaction. That will remain the same. A catalyst does not change, generally speaking. We went over a lot of this yesterday as well. I talked about like a ton of this, right? But a catalyst does, like, all a catalyst does is it changes like the activation energy required and or it causes a physical change in the system of reaction, finding a different mechanism for it to go through. Okay? Caden, if your phone won't pick up the QR code, that's fine. There's a link somewhere up there as well. If you'd like that. Scroll up a little bit. Samosa. All right, let's get started, okay? All right. In an aqueous solution in equilibrium, what is the effect on lead-2 iodide solubility when an additional potassium iodide is dissolved? I was gonna go yap some more, but then I realized that all you guys are saying is samosa, which is like cool, but like, what do you want me to say? I eat samosa. I like samosa. You guys like samosa? Food. And the song. I know you guys like the song. You guys like the food? I'm not gonna sing the song. You don't want to hear me sing the song. Okay. Perfect. Yes. Solubility will decrease. Why? What concept is this? Can someone tell me the name of the concept that we're testing real quick? Someone throw that in the chat. Yes, the common ion effect. Exactly. Right, so what happens in the common ion effect in this case, right? Potassium iodide is strong, which means it will completely disassociate. And therefore, the common ion effect, as per Le Chatelier's principle, will cause more iodide. The potassium doesn't really matter, but it causes more iodide ions in solution, which will affect lead-2 iodide solubility into iodine ions, thus pushing it back to make more lead-2 iodide solid. Parentheses S. You get me? All right. If Q is greater than K at some point during the reaction, which direction will the reaction proceed at to reach equilibrium? No bedtime. You know what time it is? Cram quiz time. Cram quiz time. Subtracting x, so here, real quick, I will talk about this. So subtracting x typically, yeah, so when you have like a large number, x is typically within the range, like, you know, like it's a guesstimate, right? Like, but it's generally, it can be within the range of like something times 10 to the negative third, times 10 to the negative seventh. And then if you have something that's like 0.3 molar, its effect on that will make it 0.2997 molar if it's like negative third, right? That'll make it negligible. That is effectively a negligible change. You can generally judge that, like, it's a judgment call in the end, but like generally speaking, when you have like a large enough, like, you know, a large number, it will make x negligible. So you can just ignore that. And the reason is because AP like doesn't typically expect to like make you do like the quadratic equation in order to solve for x. So if you are in the position where you think you'd be required to do that, chances are you can ignore x. Make sense? And then also some of these questions, guys, I am going to leave in the Q&A section, and I will get to them. We do have a Q&A section after this, so that's cool. How did 76 out of 70 people answer? Hello? Yeah, you got it right, though. Yeah, so if Q is greater than K at some point, great. You guys got it. Yeah, almost all of you guys got it right. The reaction will proceed towards the reactants. This is just something that's pretty important to note. I saw a message a really long time ago that said, like, a really long time ago, all of 15 minutes ago, that said, like, put the Q on a certain side of the equation, right? They said to put Q on the right and K on the left, and then the sign will point to the direction that the equilibrium will shift with. I really actually like that explanation. If you guys want to use that to remember it, that would be lovely. I'm so sorry I forgot who said it. I can't give you credit. I'm really sorry. But if you did, say I did it. And if you didn't, and you say that, shame on you. You did? Oh, yeah, it was you. Yeah, it was you. Anya? Yeah, that's a really good point. I like that. I like that a lot. Yeah, exactly. Kritika has a good example. Yeah, I really like that. I like the way they thought about it. If you want to remember that, that's a really great way. Okay. First. In a chemical reaction in equilibrium, which statement is correct regarding rates? What I said for the last question was that if you put Q on the right side of the problem, the direction that the greater than or less than equal or arrow effectively is pointing towards is the direction that will be favored, right? So if Q's on the right and it's pointing towards Q, that means the products will be favored. Yep. Yeah, it's just a nice little way to remember it. It's just a quick little trick. I really like this one, that Anya said that. See ya. Not everyone, please don't leave. Okay, wonderful, yeah. So the rate of the forward reaction is the rate of the reverse reaction. That's what equilibrium means. It doesn't mean, like, even though these questions are like, I would say this is relatively straightforward, it does not mean that the amount being produced of products is the same as the amount being produced. It's a rate, right? It's a rate. Just remember that, okay? All right, how does an increase in temperature affect the position of the equilibrium for the exothermic reaction? For an exothermic reaction. Ian, the quiz link was posted. It's also, I mean, here. you go. Just in case anyone still needs to join. There you go. You can also scan the QR code with any device you'd like. Scan it with your phone, your iPad, your tablet, your DSi XL. Wait, I literally age-checked myself by saying that. That's embarrassing. Anyway. Yeah, I literally just age-checked myself. Okay. Yes, exactly. So in an equilibrium for an exothermic reaction, right? So think about exothermic or endothermic reactions as part of the actual reaction. Okay? Okay, answer this in the chat. Would delta H in an exothermic reaction be on the reactant side or the product side of the problem? Where would you put it if you were to put it as either a reactant or a product? Exothermic. EX. Exactly. Exactly. Yes. It would be a product. Right. So if I'm increasing the temperature, what am I adding more of? I'm adding more of the products. What does it favor? According to Chatelier's principle, what does it favor when I have more products? It favors the reactants in equilibrium, right? Think about it as part of the problem. Think about it as part of the problem. Okay, next question. What's the reaction quotient? Yeah, good. Quotient Q used to express. I like Chatelier. I used to think about it as like when I was like learning about it initially in chem. Like I used to think about it as like a tug of war thing. I thought it was nice to think about it that way. That was cool. It's like a push and pull, right? Like what happens if you add too much? Like it's like it pulls the other way. Okay. Okay. Yeah, and there's a lot of things I remember in chem because I got scarred. Exactly, perfect. The Q is the ratio of reactants to products to reactants at any given point in time, not at equilibrium, but any other point in time, right? Because we use a different constant at equilibrium. Okay. Okay. All right. Next question. What effect does increasing pressure have on a gaseous reaction at equilibrium with more moles of gas on one side than the other? Wait, hold on. There we go. I was getting more some stuff. There's so many things in chem that I remember because I got a horrific, especially organic chem. So many things I remember because I got a god-awfully wrong on one exam and I was like, okay, that's great. But anyway, don't even worry about organic chem now. Worry about AP Chem. Vesper and hybridization. Eat that. Yeah, so I would say vocab is not super important. I wouldn't say not know names. Be familiar. Be familiar. But I wouldn't say that, like, they're not going to, like, pop quiz you, right? It's not like they're going to give you an equation pick. What is the name of this? That's not going to happen, really. So I think by far concept is much more important. Concept, and more importantly, concept application is the most important part of this exam. Yeah. They do say, like, what's the answer? Yeah, I do like what, like, yeah, I like that comment about, like, what's the answer in terms of a certain theory. That sometimes has occurred. But again, like, if you can, like, logically kind of determine, like, what would I expect from something like kinetic molecular theory, for example, then, like, yeah, we'll go through that. Okay. OPEM tips is crazy. I finished Orgo a long time ago. Yeah, I know, Yash. I would definitely agree. I felt really slow at the beginning, but like actually understanding everything, like once like everything like fell together almost, and like realizing certain like reaction terms and stuff, and realizing like certain, especially like environments, like reactions in like aqueous versus non-aqueous environments and stuff like that, I got that. You'll pick a god. I liked organic. I mean, I did research in it, right, for like 3 years. Good class. Anyway. Okay. Yeah, so if you increase pressure on a gaseous equilibrium with more moles of gas on one side than the other, well, what's it going to happen, right? If you're increasing the pressure, you're favoring something that will alleviate that pressure change. It resists change, right? And if you have fewer moles of gas on one particular side of the equation, then it'll favor the side with fewer moles of gas. Makes sense. Okay, last question. If the dissolution of salt in water is endothermic and really leads to an increase in disorder, what can be inferred about this? I can't read it. I'm going to start over. If the dissolution of salt in water is endothermic and leads to an increase in disorder, what can be inferred about the sign of delta G at high temperature? Yeah, I would say definitely with the hybridization thing, like, not that this is what I'm talking about at all right now, but yeah, names are much more important. The whole drawing, I don't think I've ever had to draw, like, ever, college included. So. All right. Here's ready to see 12 new reactions in a week. That's crazy. Those little like chart things when you like look up like when you like look up like alkene reactions, right? Like those little chart things, so good. So good. Love those little websites. The little like flow charts of them. I ate that up. Okay. Perfect. It's likely negative. Most of you guys got that right. So okay. I'll talk about this one real quick, right? What's the Gibbs free energy equation? Delta H minus T delta S equals Gibbs free energy, right? Delta H being the enthalpy, delta S being the entropy, T being temperature, right? So endothermic is a positive or negative delta H. It's positive, right? If you have a positive delta H, that means your delta H will be positive, and then your other part of the equation is minus T delta S, right? If you have increase in disorder, S will also be positive, because remember it's final like entropy minus initial entropy, which is if it's increased in disorder, you have a large number minus a small number, so that's positive, right? That means that so that's positive and that's positive. If temperature is also high, that means that you have a large positive minus like a minus another large positive. If your temperature is high enough, that means that delta G will be negative, right? If delta G is negative, what does that mean for the reaction? Is it spontaneous or non-spontaneous? Someone tell me. Someone tell me. Guys, no one's telling me. You're making me sad. There you go. Yes. It is spontaneous. Exactly. Thank you. I'm realizing that spontaneous is considerably harder to spell than I thought, and that's probably why no one told me right away. I like spont. Spont is hard. That's hard. All right. Good job. Let me move my thing. Okay. Guess what time it is? Everyone's favorite time. We stopped going over content a little bit, and you guys ask questions. And that means I'm going to answer some of your questions. Also, people like my friends in the chat are also going to answer questions. So ask away. Okay. Gibbs free energy is spontaneity. The definition of Gibbs free energy is the spontaneity of a reaction. How likely is a reaction to occur? How likely is a reaction to actually happen? Right? negative delta G or negative Gibbs free energy means that the reaction is spontaneous. It will happen. The occurrence of that reaction in a particular given system at a constant temperature or constant pressure, it will happen, right? I am, yes. I am. Irrelevantly, but like, yes, I am. Anyway, but yeah. Three major units that'll show up. I know a lot about what we talked about yesterday was really was big. I want to say, dude, I found like a chart. Let me see if I can find it. Yeah, so you can see here, I'll throw this in the chat as well. You can see how much, there you go. You can use that. You can see how much generally it works. Also, I want to plug the survey real quick right there. If you're full screen, unfull screen, and you can see it. Oh my God, can I point? There. If you're full screen, if you get off full screen, you'll see the little button at the bottom. There's a survey. Please, please, please take it. It really helps us figure out what's going on. Night 5 is a night that we really reserve for a lot of content review, as well as, FRQs, MCQs, a lot of questions and answers, a lot of quizzes, stuff like that. And we try to cater that towards you guys, right? So I just want to let you guys know if that happens, then I would love to, I'd love for you guys to put that information in so that we can personalize it to you guys and really cater to what you guys are struggling and what you guys want to see. Okay. All right. So think about the equation of delta G, right? It's the enthalpy minus temperature times the change in entropy. A non-spontaneous reaction, typically we can try to force it to occur by temperature change in certain given situations, or some reactions just will not occur, right? Spontaneous, there's certain things that in the environment, literally things around the house or stuff like that, that could potentially be a reaction that could occur that would be dangerous. However, it's not spontaneous enough that reaction will never really occur, right? So typically if we have a temperature determined reaction, that is when either both delta S and delta H are positive or when both are negative, then we can force it to occur by changing the temperature of the environment. When both delta S and delta H are positive and high temperature, yes, delta G will be positive only if, so high temp is a way of saying that the temp is high enough, right? So in essence, if you're looking at the equation of delta H minus T delta S, if the temperature is high enough such that collectively T times delta S is greater than delta H, then it will be negative for delta G, and that means it will be spontaneous. However, there is a scenario in which the temperature is not high enough, but when they just say high temp, yeah, Jasmine, that's a good question as well. When they say high temp, you can assume that means high enough. That is an assumption that you can make, okay? High temp just means it's high enough to overcome that hurdle. Practically, there's no one number. It depends on the reaction. It depends on a whole slew of things that we're not going to get into. But you can generally, on the AP exam, you can assume that. Okay? Oh my gosh, my questions are exploding. My Q&A tab is very broken. Okay, sorry. I don't know if I missed something. Sophia, I would just say FRQ answers should be bare minimum. 100% bare minimum, right? You want to get through what you get through. You want the information to be there. Understand that AP graders are not, they're also, they're not lay people, right? There are people that know AP chemistry, obviously. And when they're grading, they will also make slight assumptions when they're grading stuff. So your FRQ answers, when you're explaining, when they say explain why, it should cover the name of the concept if there is a concept. Say the common ion effect, right? If something's occurring and they're tell me why. You should, because of the common ion effect, an increase. Remember the iodide question that we just went to on a CAM quiz, right? Or Cram quiz. If the iodine is high enough, or if the iodine is high enough, it'll favor the reactants. If it'll favor the reactants, you'll create more lead-2 solid. Therefore, the solubility will decrease. That's it. Okay? That's it. The difference between standard change Standard change in enthalpies of formation. So standard change is okay, yeah. Sorry, I was like refreshing what I thought. So enthalpies of formation is specifically the delta H required in creating a particular substance from like its elemental form is essentially what they call it, right? We don't need to talk about exactly how that occurs. Experimentally, it's horrifically complicated, I promise. Don't really need to know what. But enthalpy of formation is just the effect of that. Standard change is the change in enthalpy depending on the change in enthalpy from the causing a reactant to become a product. Okay. Can I explain how the number of moles comes from in delta H? Yeah, exactly. So the delta H is dependent on the amount of a reaction occurring, right? And that means that like when you're doing delta H being like, say, like the sum of the enthalpies of formation minus, or the enthalpies of formation of the products minus the enthalpy of formation of the reactants, that means that you need to multiply the enthalpies of formation by how much of that reactant that you're using. In a reaction where, say, I have 2 moles of product being created, the delta H times the enthalpy of formation, the enthalpy of formation only accounts for 1 mole of that substance, right? So it's like, say, 100 kilojoules per mole for CH4, for example, right? If there's 2 CH4 being created, that means I need 2 times the enthalpy of formation for that particular number. So the number of moles comes directly from the reaction from the equation, excuse me. It's the coefficient. Okay? Good night, Adam. Good night. Okay. So some tricks that commonly show up in the exam are, I would say they try to do a lot of extraneous information work. That's super common. So yeah.
Yeah, hello. I'm gonna answer the KSP, the molar solubility question. So basically, KSP and molar solubility are not the same thing. I'm sorry, that was me who dropped you. That was an accident. So KSP and molar solubility are not the same thing. For an example, like NaCl, the dissociation equilibrium, I'm putting it in chat, looks like this, right? Cl minus. Right, so KSP is equal to Na plus times Cl minus, no coefficients, right? And you can say that the concentration of Na plus and Cl minus are going to be the same thing, right? And you can say the concentration is S equals Na plus equals Cl minus, right? So you can say KSP equals S squared, where S is that molar solubility, and you can find S equals square root of KSP. Now, if the salt is different, you use a different ice table and you get a different result. So if your salt is something like something really something insoluble, let's do something insoluble, like calcium fluoride. All right, calcium fluoride is insoluble. You have calcium fluoride. So the dissociating equilibrium for calcium fluoride looks like this, right? This is all in chat, by the way. If you guys can see it, please don't type. All right, this is the dissociating equilibrium for calcium fluoride. Did that message pop up, Rahi?
Yeah.
Yeah, okay. So KSP in this case equals calcium 2 plus times fluoride squared, if you can see that, right? And the molar solubility, S, is equal to the concentration of calcium 2 plus, right? But if you notice, for every 1 mole of calcium 2 plus, we have 2 moles of fluoride. So the molar concentration of fluoride is actually 2S, right? So we can replace that in our KSP expression, replacing Ca2 plus with S and F minus with 2S, and squaring that, we have KSP equals, make sure you have the parentheses there, 2S, the whole quantity squared, we get KSP is 4S cubed. And then to find S is our molar solubility, the same thing as the concentration of calcium. S equals KSP. The parentheses are really important, guys. Now you can do this for a different salt. For an example, another salt, bismuth sulfide, your KSP would be equal to 2S squared times 3S cubed. which would be 108 s to the fifth. If anyone wants to go ahead and try to do that themselves and see how that works out, they should go ahead and do it. But that is the relationship between molar solubility and KSB. It depends on the kind of salt that you have.
So Q melt and Q heat, yeah, for that question, Q melt and Q heat really just depends on, you have to look at the graph, right? You have to look at what's occurring on the graph. So Q melt will occur within a standard state change, right? The actual temperature is not changing anything, but it occurs over one particular state change, right? If something is literally melting, right, then you'd use Q melt. However, heat is when there's no phase change, when there's no state change, right? Something is not actually melting or anything like that, but the substance is increasing in temperature, right? Like Q equals MC AT. There is an delta T, excuse me. Q equals MC delta T. There is a delta T occurring, right? But since there's no temperature change in Q melt, that's why we use delta H times the number of moles, right? So you use both. In the example that we gave, the FRQ that we gave, that was actually a really good example of where you'd have to use both, right? Where I heated a substance from, it was 25 degrees Celsius to 159 degrees Celsius. And if I heated it, and then also 159 degrees Celsius happened to be its melting point, and it also completely melted, that's when you'd have to use both Q melt and Q heat, because Q heat works from the temperature change from 25 degrees Celsius to 159 degrees Celsius, and Q melt specifically is along that particular phase change, and there is no change in temperature. And that's why we use the enthalpy of fusion. Okay, that's a little bit of a vague question. However, I'll do my best. Multiple choice questions are generally some of the more difficult questions to answer. And the reason is because people tend to make little mistakes, people tend to guess, and then you can't get partial credit like you can on FRQs, right? So I would say number one thing is time. Watch your time. Phase it out. Don't go too fast. Don't try to rush and think like, oh my God, this is easy, and then try to go fast. It happens. However, don't try to go too slow. That also happens. Depends on the kind of test taker you are. I don't know you personally. But yeah, so remember to do that. And then also another thing is try to add a definition to every single problem you work for, right? You can't just look at a problem and like you won't necessarily know the answer right off the top of your head. That doesn't always occur. And that's fine. There's no problem with that. But I would use that and say, okay, sorry, that scared me. Let me look through and then try to assign a definition. This product this is testing the common ion effect. So what happens when it's testing a common ion effect? And then you think about that topic. And then once you think about the topic, then hopefully you can get to an answer for that question. Those are some of the better tips that I got.
Oh my God. I wanted to do the more general questions because I really miss being on screen. I was on screen last year, guys. But oh, Rahi, do you want to repeat the tip again before the definition one?
I just said the biggest thing is depending on the test taker that you are, watch your time. If you're someone that goes fast, then make sure you're not going too fast. If you're someone that goes slow, make sure you're not going too slow. I try to divide up the test, right? Take the amount of, I don't even remember the times, but take up like the amount of questions on the exam and also the amount of time that they give you for the multiple choice question, divide it in half, and understand that you should probably be halfway through the exam when you hit that halftime. You shouldn't be way too far ahead. You shouldn't be 7/8 or 3/5/6 or whatever other fraction done at the exam. And you shouldn't be way too behind, right? So like divvy up your time and make sure you're spending enough time on each question that you're really properly thinking about it and catching your own mistakes, but you're not too slow and you are going through the questions that you like can't go, like that you don't know. It's okay to skip questions. That's not a problem. Don't get freaked out by that. It happens. You're not expected to know everything.
Yeah, and then with the question that's on the screen right now about how many sentences should an FRQ be, so a lot of with the chem FRQs, they're like math problems, but then there's also the conceptual ones. You basically want to give enough detail that you answer the question to its entirety, but also just like, I mean, if you have time, put as much detail as you want, but at the end of the day, like you have a limited amount of time and there will probably be something that you're not as confident on as the other ones. So I mean, like what I would do is like I would answer the question and then go back and then like reread like the FRQs. And if you have time, you can add more detail, but like you don't have to keep repeating yourself. I mean, like someone who repeats themselves 5 times and gets the point after the 5th time gets the same amount of points as someone who just did it the first time. So, I mean, like, if you have like 2 ways of explaining it, then like do that, but just don't repeat yourself over and over and over again. Oh my God. This is like illegal. Oh wait, it's not even like posting. Can
No,
you
there's
see
another one
like,
on
okay,
screen. There's
there's a
another
question.
one on screen. Hit that one.
I'm like, okay. Oh, okay. Anyways, it says like, test proctors will not tell us to erase or clear the memory of our calculators. This is true. In my experience, I've had like every single test proctor tell me to clear my memory, and then like depending on like I took mine in like small rooms, so like they would go around and like see if like people like it says like RAM cleared. I personally would not like try it. Like I don't think it's worth getting your AP exam score canceled if like they somehow figure out that you're doing that. And it's cheating. Like, guys, like we do not support this.
Yeah. I also would not do that for sure.
Yeah, because like I mean like not only are you harming you, but like you're harming like everyone else and that's also taking the exam. Because if they find out that someone, if they suspect someone is cheating within the like exam room, then they're canceling everyone's score in the exam room. So you don't want that. Rahi, I'll just give you all the actually informative
The
questions.
real questions? Yeah. Let me take those.
Yeah.
Yeah, so Q melt is not the heat of formation. The heat of formation is the heat of fusion, heat of formation, etc. is the delta H value of a particular either state change or something like that, right? Q melt is like the Q is energy, remember, right? Is energetically how much energy in typically joules or kilojoules that you're required to cause something to occur, right? And Q is like, again, like it's that lowercase q in this case is something that like is it's dependent on occurrence, right? Q is the amount of energy required to either when you're just doing like Q heat, right? When it's required to heat something up, right? It's how much energy you're required to inject into the system. For Q melt, right? How much energy is required for you to melt something? It's not the heat of fusion. However, you use the heat of fusion times how much you have to know how much you have, because heat of like those like delta H's, those are all in terms of like per mole typically.
And I also feel like that answers the other question pretty well about like heat of formation. And I think we mentioned that earlier.
I would agree.
Does anyone else have any like
any other questions? Otherwise, we will end it off.
And stick around for a few more minutes. Tomorrow's gonna be pretty great. I think we're doing acids and bases tomorrow, everyone's favorite.
I know.
And then we're doing unit 9, which is like a smush of like a bunch of stuff.
Yep. And I am talking again, so maybe people will finally start to get sick of me. Who knows? But we'll see.
And for those of you who are still here, make sure to take the survey that's down below. Again, like Rahi said earlier, it really helps us with figuring out what to do and what you guys want for night 5, since that's dependent on a lot of you guys. There is, I think like how we have it set up is that we have like general concepts, plus like an FRQ from each unit. And then we have general advice before test taking, and then we can either do a cram quiz, or if you guys want specific like questions to be done, like for example, I know like a lot of people were struggling with like the ice table and the solubility table earlier tonight. We can always do another question like that. So yeah. I'm TAing a current class right now called Analytical Chemistry, which is basically Gen Chem 2, and it's just like Unit 8 and 9, but like super
okay.
in depth,
Yeah,
and it's
right.
like really crazy.
All right.
Anyways,
I think we are good to end it off. Go ahead.
I think so too.
All right.
Do you want to close us off?
Yeah, sure. Just another plug for us. Do follow us on all socials. Keep updated. I feel like such an influencer when I say that. But yeah,
I mean,
but
we
thank you
are
guys for joining.
influencers, though.
I know, right? Thank you guys for joining. Tomorrow we'll go over units 8 and 9. And yeah, so we'll do that. And then May 5th is going to be our big old finale. There's no content coverage there. It's mostly catered towards you. We're going to be doing a lot of FRQs, MCQs, cram quizzes, such like that. So we will see you guys tomorrow night. Thank you guys for coming. Thank you guys for having me. Bye.
Bye, guys.